you. Are you ready, Glenn? You can go ahead and share
Yep,
your screen.
I'm okay. Okay, can you see the presentation?
Yes, hold on a sec. And Sarah, can you introduce this special session?
Sure. Yeah. So the motivation behind this session was a couple different conversations with folks about how there seems to be a lot of development in the ocean model hierarchy realm, and we just wanted to highlight what's going on, around the country, and then use that information to prompt a little discussion at the end.
Okay, Glenn, go ahead.
Okay, cool. Yeah, thank you for the opportunity to speak today. I'm Glenn. I'm a graduate student in the MIT Hui Joint Program. Today, I'm going to present our work on understanding the drivers of Atlantic multi-decadal variability using a stochastic model hierarchy. This was recent. I want to acknowledge my collaborators, Youngo, Claude, and Jian. And this has been published recently in the Journal of Climate. QR code is on the lower left. So to start off, just quickly defining Atlantic multi-decadal variability, or AMV. Essentially, this is the quasi-periodic oscillation of sea surface temperatures averaged over the North Atlantic, and it has a characteristic horseshoe-like pattern of warming with a maximum in the subpolar region. One of the interesting things about this phenomenon is there's still an ongoing debate as to the relative importance of ocean versus atmospheric dynamics. For example, some believe that AMV arises mainly through ocean dynamics, such as variations in port heat transport due to the Atlantic meridional overturning circulation, while others believe that you can get AMV primarily through atmospheric dynamics, such as through the dominant mode in the region, the North Atlantic Oscillation. So one of the challenges of understanding AMV is that since the observational record is so short, we have to often rely on model simulations to make statistically robust statements about this phenomenon. And to really try to disentangle these two components, we often rely on simplifying one of them. So an example of this approach is if we simplify the ocean component and use a slab ocean model. So a slab ocean model is essentially an atmospheric GCM coupled to a slab of fixed depth. And you can see here, looking at the slab ocean temperature equation, that the temperature is primarily determined by the net heat flux between the atmosphere and the ocean. There's no interactive ocean dynamics, no communications between grid cells laterally or vertically. And additionally, there's an additional heat flux correction term that's applied to the model to obtain a realistic seasonal mean SST climatology. And generally, the mixed layer depth or the thickness of the slab is fixed in time, though it can vary in space in certain models, such as CSM1, which we'll be using today. So kind of the main takeaway from this is that the slab ocean really allows us to understand what does SST look like in a world without ocean dynamics. So in a kind of famous 2015 paper, Clement et al. Found that slab ocean models on the right were able to reproduce both the spatial and temporal characteristics of AMV that are comparable to observations on the left and fully coupled models in the center, raising the question of, is ocean circulation really necessary to generate AMV? More recently, there's been a lot of work that has found that slab simulations actually have higher SST variance compared to fully coupled models. This suggests that the addition of ocean dynamics acts to damp SST variability, particularly at low frequencies. And here's part of where the challenges of using the slab approach arises, in that when we remove ocean dynamics altogether, it becomes a little bit challenging to determine what exact processes lead to these differences between slab and fully coupled simulations. So there's a need for a more transparent process-based way to understand why, what's the contribution of ocean dynamics to AMV. So to do that, we return to the classic stochastic climate model proposed by Hasselmann in 1976. In this very simple model, the evolution of temperature within the mixed layer depth is determined in a simple equation with just two terms. The atmospheric forcing of the system is on much shorter timescales, so it can be parameterized as white noise of a certain amplitude. And given some anomaly, that anomaly is damped to the atmosphere via heat fluxes, and the strength of that damping can be determined, can be parameterized as this sort of linear coefficient, lambda sub A. So essentially, this model is pretty successful at capturing the mid-latitude characteristics of SST, but all these parameters do vary on a seasonal basis. So one of the questions of this work is trying to understand how seasonal variation in these parameters impact SST variability. Furthermore, there's also the consideration of mixed layer entrainment. So in the wintertime, the mixed layer temperature anomalies are mixed much deeper into the ocean. However, during the summer, there's a formation of a shallow summer thermocline. This thermocline effectively insulates temperatures below the mixed layer from further interaction with the atmosphere. The following fall, as the mixed layer deepens again, the anomalies are re-entrained back into the surface. This affects conditions the following year and allows a year-to-year recurrence or reemergence of conditions. This can be described in the stochastic model with the addition of an entrainment term. Note that there are both forcing and damping components. So one of the goals of this work is to explore how does the addition of this entrainment term impact the characteristics of SST variability, and does this impact extend out to multi-decadal timescales? So the equation looks pretty complicated, but there are only really 3 input parameters: the amplitude of forcing, the heat flux feedback, and the mixed layer depth. And I'm going to go really quickly over how we estimate these parameters, but if you have any questions, feel free to ask me at the end. So for the forcing, we essentially do an EOF analysis on the stochastic component of the heat flux in CSM1. We replace the principal components with random white noise. This essentially allows us to have forcing that is random in time, but has spatial coherence and varies on a monthly basis. For the heat flux feedback, we use a statistical covariance-based approach from the literature, and for the mixed layer depth, we use the seasonal climatological cycle from CSM1 full. So it's repeating on a 12-month cycle. We estimate all these parameters from CSM1 pre-industrial control runs, and we compare the resultant SST to these respective simulations to really try to understand what's going on in the physics of this model world. So we've developed a hierarchy to answer 3 key questions, and I'm going to walk you through how we're going to accomplish this. So the first question is we're trying to investigate, again, how the seasonal variation in these model parameters impact variability. To do that, we start with a fixed, the classic model with fixed inputs, and we individually add in seasonal variation in damping and forcing together in level 3, which is analogous to the slab simulation, and then variation in mixed layer depth. To understand how entrainment impacts SST variability, we compare what happens with and without the entrainment term. Additionally, we can compare the entraining stochastic model with the full physics ocean model, CSM full, and try to understand what is the contribution of the dynamics beyond entrainment. Finally, we focus on these 2 comparisons to see if we can recover the spatial characteristics of A and B using stochastic forcing. So to kind of get started and to really understand what's going on, we've chosen a single point in the subpolar gyre for 3 reasons. It's located where the A and B is maximum in the CSM1 full simulation, so the signal is the largest there. It's also away from advective regions, like the western boundary current, allowing us to focus on the interplay of local processes. And finally, there's a very typical seasonal variation in parameters here. So notice that all the parameters are high in the winter and low in the summer. We integrate each level of the hierarchy for about 10,000 years at this point. And first, we're going to talk about the persistence of SST. So here, I'm showing the February SST lagged autocorrelation. We choose February because it's the month of the deepest mixed layer depth at this point, so it allows us to understand this extreme case where we expect temperatures to be the most persistent. So the canonical solution to the stochastic model is an exponential decay of time. So this comes as no surprise. But when we look at what's happening in CSM slab at the same point, you'll notice that there's a sudden slowdown in decorrelation that happens during the summer months. So the reason for this decorrelation becomes clearer as we advance up the hierarchy. Specifically, when we look at, it's the addition of seasonal variation in forcing in cyan and red that allows for the reproduction of this sort of slowdown in decorrelation. And so what exactly is happening here? So if you remember from the seasonal variation of parameters, the stochastic forcing is much weaker in the summer. However, in these slab-like configurations, the mixed layer depth is constant. As a result, you have this weaker stochastic forcing and more persistent conditions that happen during the summer, suggesting that slab-like configurations have this sort of unrealistic SST persistent. And to bring that home, what happens when we add in seasonal variation in mixed layer depth? So here in the magenta line, you'll see that when we add that in, this persistent shoulder-like feature disappears. And to kind of explain that again, in the summertime, we have much more shallow mixed layer depths. So the system has much lower heat capacity and is more sensitive to forcing from the atmosphere. So the memory of that is no longer present, and we no longer have persistent conditions through the summer months. So going on extending that a little bit further and comparing now to the full physics ocean model, we see that the simple addition of seasonal variation in mixed layers isn't enough to capture the winter-to-winter recurrence of conditions. And it's only with the addition of the entrainment term that we actually begin to capture this behavior. And it does pretty well considering that's a simple model with just 3 terms. So what about at longer timescales? Now we're looking at the power spectra in this case, going from 2 years to 100 years. And let's just focus on what happens when we add in entrainment. So here I'm showing the full physics ocean model compared to the stochastic model without entrainment. And you'll see that there's an overestimate at interannual timescales and an underestimate at lower frequencies. When we add in entrainment, we see that there's a slight improvement, but it still doesn't quite capture everything. The main effect of adding in entrainment is a damping at interannual timescales. And there's still an underestimate that's going on at low frequencies, suggesting that the dynamics beyond entrainment really come into play at these lower frequencies. So we've been looking at a single point in the subpolar gyre, but what about some other? We can also repeat this analysis by integrating this model at every other point in the basin and looking at some area average quantities. So here I'm focusing on some key regions of the A and B pattern, the maximum in the subpolar gyre, the extended lobe along the eastern subtropics, as well as the minima in the western subtropics. And we're going to focus again on the power spectra and examine what happens when we add in entrainment. So in the broader subpolar gyre region, we see a similar story where there's damping at interannual timescales and enhancement at multi-decadal timescales. However, in the western subtropics and the eastern subtropics, we see that while there's a similar thing happening, this actually widens the disagreement with what's happening in the full physics ocean model in white. So this is no surprise, as in this region, there are other ocean dynamics that are not included in the stochastic model, such as advection and subduction. But again, the kind of common feature here is that entrainment seems to be enhancing variance at multi-decadal frequencies. So the next step would be trying to understand how different contributions of other processes in the subtropical regions could lead to better agreement with the full physics ocean model. And we've been talking a lot about the temporal characteristics. So what about the A and B spatial pattern? So here I'm comparing the CSM slab and its analogous stochastic model hierarchy. So we can see here that the stochastic model does a pretty good job of capturing the major features of the canonical horseshoe, but underestimates its amplitude. When we compare CSM slab and CSM full, we see that there's no longer a negative pole in the subtropics, and the maxima kind of shifts to a more concentrated region in the subpolar gyre. So the question is, when we add in entrainment to the stochastic model, do we get a similar effect? The answer is kind of. Adding in entrainment damps things way too much, and also causes the maximum in the subpolar gyre to shift to the northeast where the mixed layer depth is maximum. So this kind of suggests that the missing dynamics here really come into play when considering the small scale details of the A and B pattern, as well as getting the correct amplitude of variance. So sort of the main takeaways, I think I'm kind of running a bit short on time, so I might just leave this here and open the floor to any questions you might have. Thank you for listening, and I have the link to our paper on the lower left. I'm happy to take any questions now.
Any question in the room?
Just a clarification. So would you argue then that because when you include the entrainment, you get much weaker anomalies in the North Atlantic, that the kind of Clement et al. Study that found similar amplitude anomalies to the couple model is kind of getting things right for the wrong reasons?
Right. Yeah. There's because of, for example, in the slab models, because of that sort of fixed mixed layer depth, there's sort of more, I guess, the kind of like more ocean memory in that region. So you could see it as getting sort of the right answer for the wrong reason, I guess. And it'll be interesting to kind of interrogate it a bit more, and I guess quantify how much that impacts. Yeah, I guess kind of quantify that a bit more rigorously, but.
Sarah, there's any online question?
Yeah, I shared a question. Yeah, thanks for the nice talk. Do you have any idea why entrainment is damping too much in the stochastic model? Does it have anything to do with just the lack of ocean dynamics that ramps up the amplitude of the anomalies, or is that just kind of an unrelated problem?
Right. So the idea of entrainment damping too much in the stochastic model, I need to think a little bit more about that, and we haven't investigated that in much more detail. There has been other works in the literature that have found that the primary contribution of entrainment in sort of these heat budget calculations is to damp anomalies, particularly in the subpolar gyre region. But yeah, I haven't kind of specifically investigated within the stochastic model if it's damping too much for, yeah, I haven't quantified that specific amount of damping, I guess.
No question?
I think this is a comment. If you have a first order autoregressive process and you are perturbing the autoregressive parameter, it will act as a damping. So, so that would then give you the variation. You could even use this to deduct how much perturbation you need to get the correct damping. You could use the fluctuation dissipation theory. So just as a comment.
Oh, no, thank you. Yeah, I'd love to talk more about that if we could, yeah, potentially talk after, or
Okay, thank you.
thanks for the comment though.
All right, we'll move on to the next talk. Will given by Tianyao Xu. Okay, Tianyao, you can go ahead, share your screen.
I don't know if we can, is he talking?
Yeah.
You can hear,
Okay, right now we cannot hear you.
but it also doesn't look like he's muted.
No, we still cannot hear you.
Can you hear me now?
Yes.
Okay. Okay. Hi, everyone. I'm Tianyao. I'm happy here today to share my work. When I was in UCI, and the work is done with Francois and Gudrun. So the title is A Hierarchy of Ocean Models Coupled to CESM1. And this is the work that has been published. Sorry, it's actually 2022 in James. And here it's a list of acknowledgement of different resources that I had in the past, including Yannick Pins, Johan Kwan, Paul Kushner, and the DOE. So to start off this talk, I will show you two different responses. And this is the response of the ocean model, of atmospheric model, the annual mean precipitation rate, if the atmosphere is coupled to two different ocean models, which is the slab ocean model and the OGCN. In this case, is the POP2. And you can see that in the slab ocean model, the ITCs actually shifted northward in the north hemisphere, whereas in the OGCN one, it doesn't shift at all. Actually, it contracts and intensifies at the equator. And I think Glenn did a really good job introducing what slab ocean model is. So basically, slab ocean model is a land model. It's an ocean that doesn't flow. So it doesn't respond, the ocean flow doesn't respond to the atmosphere So there's no horizontal transport response at all, whereas OGCM contains everything. So it's very complicated, and so there's a really big gap between them. So apparently, the ocean process modulates the ITCZ shift. So the question here is, how do oceanic processes modulate ITCZ shift, specifically when the Earth is forced with Arctic sea ice loss? And this is actually not a new question. This is a classic one that raised several years ago, and the idea here is that whenever there is a warming in the North Hemisphere, the ITCZ will have to shift north so that the energy, so the circulation, anomalous circulation could send excessive heat into the Southern Hemisphere to rebalance the interhemispheric heat budget. So if the hemisphere is coupled to the slab ocean model, then all the action have to happen in the hemisphere. So there's a really strong ITCZ shift in general if the ocean is not reacting. But if the ocean can react, such as ocean heat uptake, either uptaken by the AMOC or the mixed layer, then you can directly inhibit the reaction by doing this. But a really popular theory upon this damping effect is actually the Ekman flow. So here I show the response of the zonal wing anomaly in the gray arrows, and the cross-equatorial wind is shown in the red flat arrows. And you can see the corresponding driven Ekman flow shown in the blue is transporting the heat southward across the equator. So because the ocean is helping sending the heat to the southern hemisphere, so the atmosphere doesn't have to do that much. So that means the Ekman flow is damping the ITCZ shift. But in the actual Earth, all these processes will happen all together. So it's a little bit hard. You can theoretically kind of verify this idea, but if you want to kind of see these things in the actual Earth configuration, it's kind of hard because they all happen together and one might shield another. So a way to resolve this is to use the hierarchy, model hierarchy. And here is the model hierarchy we developed. It's called the EMON model hierarchy. EMON stands for Ekman Mixed Layer Ocean Model. And basically, it's a model that resolves two different processes. One is the varying mixed layer depth in time. And the other one is the Ekman flow that respond to the wind stress. So because in this particular design, I can turn on or off each processes independently. So it actually effectively formed 4 different models, but only 3 of them will form a strict hierarchy in terms of the complexity. So if you turn off both, that means you have a constant mixed layer depth and non-responsive ocean flow. So that gives you the slab ocean model. And if you turn on the mixed layer model mixed layer, the temporal variation of mixed layer depth on. So that gives you the mixed layer model. And this is very similar to Glenn's mixed layer model, but we have a little bit diffusion over here so that they can be comparable. And on top of it, if you even turn on the Ekman mixed layer, the Ekman on, then that gives you the EMON. And on top of everything, we still put the POP2, which is the OGCM on top of everything, serving as the truth of the simulation. So these 4 model forms the hierarchy. So here I need to introduce the Ekman flow parameterization, which is introduced in Codron 2012. So basically, Ekman flow here is the result of the force balance between Coriolis force, friction, and the wind stress. And in this particular formation, because you introduce the friction, you can resolve the vanishing of the Ekman flow at the equator. So there's no singular point in this parameterization. So the result, the flow is a superposition of the traditional Ekman flow and the frictional flow. And here you have to notice that the frictional flow is particularly important at the equator. And we picked this number so that the frictional flow will dominate between 5 to 5, and it will gives you a proper upwelling at the equator. That's how this epsilon number is chosen. So here, we come to the perturbation experiment, which is Arctic sea ice loss. And here we force the simulation with the RCP 8.5 sea ice loss. So blue here is the annual mean sea ice thickness in the pre-industrial control. And the red here is the sea ice in the last 20 years of the 20th century in the RCP 8.5. So the difference between them is how much sea ice loss we forced using the nudging method. And on the right, I just want to show you all the system quickly starting to equilibrate after 80 years. So we pick the last 100 years as the statistics on the climatological mean in the sea ice loss, and subtract the pre-industrial mean out as the response. Okay, so I think it's enough to show the response of SST and the precipitation to demonstrate how different they are. So first of all, the SST in general is similar because there is a very strong warming in the northern hemisphere, because that's exactly how we force the sea ice loss, but their precipitation response is very different. So the top and the bottom are the precipitation response in the OGCM and the slab ocean model, in which we kind of understand what happened because their slab ocean model doesn't cause any ocean heat transport. So it has really pronounced ITCZ shift. But in the mixed layer model, ITCZ shift is damped because the mixed layer depth is effectively deeper in the mixed layer model, because in the winter it's much deeper than the annual mean. So it introduced more effective ocean thickness. So that's why it's damped in the mixed layer model. But in the EMOM what is very interesting, because in the EMOM we really don't see the damping of ITCZ shift. Instead, it actually amplifies it. So if you see the zonal mean of precip on the right, the red is the shift in the precip response in the slab ocean model, and the blue is the precip response in the EMOM, which is almost double the strength. I mean, in terms of the precip compared to slab ocean model. So this is very different from what we initially expected. So if you dig into the ocean heat transport, it's even more comparable in this way, that the slab ocean model here the three lines, the black line is the total heat transport, and the breakdown is the red atmosphere heat transport, and the blue is the ocean heat transport. So you can see in the slab ocean model, all the heat transport at the equator is done by the atmosphere, whereas in the OGCM, the heat transport at the equator is mostly done by the ocean, and in particular, it's in Atlantic basin. So that's a really strong signal of AMOC action. So we know that in the OGCM, there's less effect of ECMA because the AMOC is damping everything. It's transporting the heat totally. So there's no role for the atmosphere to act. But for the EMOM, you can see the ocean heat transport is not really helping the atmosphere. It actually transport the heat to the north hemisphere. So that means atmosphere had to react even more to rebalance the interhemispheric energy imbalance. So that's why there's more ITCZ shift in the EMOM. So I will do really quickly. So this is the final slide that after we digging into the reason, we think the reason is because there's a strengthened trade wind across. So it's not really trend. There's a strengthened meridional wind across the equator, and especially it's blowing the ocean to the north, causing the frictional flow and associated ocean heat transport. So if we add that understanding into the image on the right, that means we are causing a meridional wind anomaly and the frictional oceanic heat transport to the north, which causing more heat transport into the northern hemisphere. So that's kind of the thing that the traditional argument is kind of omitting this frictional effect. So if you look into the horizontal map, you can see the black arrow is the surface wind and the green arrow is the associated ocean flow. So it's actually advecting SST into the north hemisphere, causing the heat convergence in the north hemisphere. So that we strengthen the ITCZ shift in this case. So the take-home message is that we construct hierarchy coupled to CSM. So we applied that to the Arctic sea ice loss to study the modulation of the ocean. And in the OGCM, the AMOC is take up the heat strongly, so ITCZ shift is inhibited. And in the Ekman allowed model, the frictional flow will amplify the ITCZ shift. However, this outcome is sensitive to the form of Ekman parameterization, specifically the choice of epsilon or the frictional term will change your answer, the extent of the ITCZ shift. Okay, so I think this is all my talk. I will take the question from here. Thank you.
Question in the room?
So I guess I'm wondering, is the takeaway then that just given the role of AMOC, that really none of these idealized configurations are suitable for looking at the response to sea ice loss?
Sorry, can you say that again? I couldn't hear you clearly.
Yeah, I guess I'm wondering if the overall conclusion here, given the role of AMOC, is that actually none of these idealized configurations are up to the purposes of looking at the response to sea ice loss. Or
yes, yeah, I think that's a good point, because I think that's also connected to how we force the sea ice loss, because in this configuration, the sea ice loss is completely caused by the pseudo heating directly to the sea ice model. So there's a really strong freshwater flux into the ocean, so the AMOC respond really strongly. But in the reality, the sea ice loss is caused by the CO2 forcing. So the response was supposed to be different. And the second thing is that in a lot of simulation, if you force the sea ice loss with the quadruple CO2, let's say, then usually after a few hundred years, the AMOC will restore itself to a pretty good extent. And so if you're actually looking at the equilibrium kind of the solution, sometimes AMOC actually doesn't, in terms of the heat transport, it doesn't change that much, especially at the equator. So that will be a window of opportunity to think of the ocean response as a really surface reaction rather than a deep ocean. So I think one of the message here, I didn't write it out, is that AMOC is important, but mostly in the transient response. It may not be as important as it is in the equilibrium ones. Yeah, I know it's a long answer, but yeah.
Thanks.
Any other question?
Sarah, question.
Yeah. And Sarah has a question in the chat. It said, does the nuclear depth vary seasonally in the EMO?
Yes, that's a good question, Sarah. Yeah, it varies seasonally. It's prescribed seasonally, so the mixed layer depth doesn't respond to the change of the wind stress in the atmosphere. And so this is not the same. This is more similar to Glenn Liu's mixed layer model, but not the same as the pencil model, which Dr. Yoho Kong will introduce later.
Thank you. Okay, now we move on to the next talk. It will be given by Chengfei He. Okay, yeah, you need to unshare your screen.
Hello? Could you hear me and see my screen? All right, so yeah, hi everyone. Thanks for having me here. I'm Chen Fei. So currently I'm a postdoc working with Amy and Mark in the University of Miami. So today I'm going to talk about a recent published study on GRL that shows that there is a warming hole could arise in a GCM without ocean circulation. Basically the slab ocean model. I think Tian Yao and Glenn has introduced it quite a bit. So the background here is very interesting. So on the global warming, there is a cooling center in the subpolar North Atlantic. And this has been hypothesized to be caused by the slowdown of the AMOC, as well as other ocean processes like the gyre, as well as the Eichmann transport. Both of them are wind-driven circulations. So, but, so the SST actually physically is affected by both atmosphere and oceanic processes. Then we can ask, so what is the role of the atmosphere in the North Atlantic warming hole? So recently, so there is an interesting study by Lee et al. They just focus on the local environments and neglect the ocean heat transport in the North Atlantic warming hole regions. And they use a simple model to analyze the temperature change in the North Atlantic warming hole regions. So they found that there is a surface heat flux. It is decreasing over the North Atlantic warming hole regions. Therefore, in this case, this decreasing of the surface heat flux could produce 50% of the cooling in the warming hole. And then they add the entrainment of the mixed layer, and again, it could produce another 50% of the cooling. So in total, it seems like the local environments could produce the whole warming hole without the change of the ocean heat transport. Then this comes to our motivation. So first is, Lee et al. Is using a simple energy balance model. Then what if in a GCM, like a slab ocean model? In a slab ocean model, we don't have dynamic ocean currents. And the second is, so if we have a warming hole in the slab ocean model, then how does the surface heat flux mechanically excite this North Atlantic warming hole? Because in the slab ocean model, the SST is totally driven by the net surface heat fluxes. So this comes to our method. So we are using the CESM slab ocean model, and we run 9-member historical simulations from 1920 to 2005. And the forcing in our simulation is the same as the CS1 large ensemble. So we will compare our simulation with the CS1 large ensemble as well as observation. So in this case, from SOM to the fully coupled model, we have a model hierarchy. We could understand the role of the atmosphere. So here is the results. What I show here, it is the SST trend in the observation and the CSM1 large ensemble from 1920 to 2005. So what do we see here? Actually, the fully coupled model reasonably reproduces this warming hole in both the intensity as well as the shape of the warming hole. And what I show here at the bottom, it is the warming SST trend in the slab ocean model. What we could see is here, there is also a warming hole in the slab ocean model. However, there are some differences between this slab ocean model simulated warming hole and the observation and fully coupled model. The first is the intensity is different. The cooling in the slab ocean model seems like only 50% of the fully coupled model and the observation. And the second one is that the shape of the warming hole is quite different. In the slab ocean model, so the shape is more like a bullet, but in the fully coupled CSM and observation, so it looks like a diamond or like a fingerprint. So we will return to this pattern difference at the end. So even though the absolute cooling, it is just 50% in the slab ocean compared to the observations. However, this warming hole is actually relative to the global warming. Therefore, we define the warming hole index as the warming hole temperature minus the global SST. Then we plot this warming hole index in the observation as well as in the models. Now we could see actually right now the slab ocean model is quite close to the observation, and both of them have a 0.8 or 0.9 degrees per century cooling. And it is because even though the warming hole temperature is kind of 50%, But the global warming in the slab ocean is much stronger because the ocean in the slab ocean model is shallow. Therefore, so the warming is much stronger. And as a result, it produces a quite consistent warming hole index in the slab ocean model. So to summarize here, we found the absolute cooling in the slab ocean model is like 50%. But relative to the global warming, the slab ocean model actually produces a quite good job compared to the observations. So then the question is, how does these surface heat fluxes mechanically excite the Atlantic warming hole? So like I said before, the SST in the slab ocean models is purely driven by these net surface heat fluxes. And for this net surface heat flux, we are able to decompose it into different physical components. So as a result, we are able to understand how these physical components change the net surface heat flux, then change the sea surface temperature trend. So for the latent and sensible heat, it is easy because we have this bulk formula. So we basically linearize these bulk formulas, so we are able to know what kind of components are changing the latent heat and sensible heat. But for long wave and short wave, so these radiative calculations in the model is complicated. So there is no explicit formula there. So, but if we think about this linearization process, actually it is a first order Taylor expansion. So basically it is the more linear regression. So then we just regress this long wave and short wave onto the different physical variables here. So overall, we found there are 6 variables that could affect the net surface heat flux, then the SST. They are the surface wind strength, the surface temperature, relative humidity, LC temperature difference, as well as cloud cover and greenhouse gases that will affect these radiative forcings. So here is the full decomposition of the SST trend in the SOM. So this is most can be part in my talk, so please pay attention. So we first focus on the first row. In the first row, I decompose the SST trend into different components in different surface heat fluxes. Then from second to the bottom, I decompose the surface heat fluxes, the SST trend in these surface heat fluxes. So that means if we add from second row to the bottom, then we get the first row. And if we add the second column to the rightmost column, then we get the first column. So here we see these 6 different variables actually lead to very different SST trends. And if we add them together, we get this total. And among these 6 variables, actually, there are 3 groups here. The first one is the cooling group because it is mostly cooling, and it is associated with the surface wind strength and the LC temperature difference. And the second one is the neutral group, you call it, because when we average, so average in the region, so it mostly becomes 0, and it is associated with relative humidity and cloud cover. And finally, it is the warming group. It is due to the SST itself as well as the greenhouse gases. So in the next few slides, I will walk through these groups to illustrate the mechanism behind them. The first one is the role of the wind strength. So the wind strength leads to cooling mostly in the east basin, and then the cooling extends into the interior ocean. We investigated the wind trend in the subpolar Atlantic region. We found actually in this region, the wind strength is increasing. So physically, as a result, an increase in the wind strength will enhance the sensible and latent heat. So in this case, it will try to export energy out of ocean, therefore leads to the cooling. And we also compare our increasing surface wind strength with the reanalysis. So we could see here, both of them shows a very increasing trend, even though in the reanalysis, so there is a strong interannual variability there. Then the second one is the LC temperature difference. So the LC temperature difference leads to a cooling that mostly in the west boundary and then extend to the interior ocean. And we found this LC temperature difference is actually also related to the surface wind. What I show on the left, it is the correlation between the LC temperature difference and the surface temperature advection. So we see here they are highly correlated in these warming hole regions. Physically, it is because the surface vastly intensifies, so it will advance more cold air from high latitude or nearby continent to the open ocean. In this case, it will amplify the LC temperature difference here. Then the amplified LC temperature difference will increase the sensible heat and the latent heat to export energy out of the ocean, then lead to this cooling. So again, this one is related to the surface wind. Now let's come to the neutral group. In this neutral group, so the cloud and the relative humidity lead to a kind of a zonally dipole response. And if we add them together, so we largely get a neutral response. So we found this cloud and relative humidity are also related to the westerly, but it is at high level. What I show on the left here, the shading is the climatology for the jet, and the contours are the trend of the jet stream. So we see during this simulation period, the jet shifts northward and also elongates zonally. As a result, in the east basin, so the jet increase and the storm track increase, and in the west basin, it decreases and the storm track decreases. So the cloud cover actually changes in the similar way. So the cloud cover increase in the east and decrease in the west. So as a result, it perturbs long wave and short wave, therefore lead to this dipole response. Also, the relative humidity changes in a similar way, then it leads to this opposite response due to the latent heat. Therefore, they cancel each other and lead to a largely neutral response. And finally is this warming group. For this warming group, actually, it is very intuitive because the net effect of the processes I discussed above all leads to a cooling response. Therefore, this TS will reduce in the latent heat. However, this acts as a negative feedback because a TS reduces in the latent heat, then it will try to reduce the latent heat out of the ocean. Therefore, it induces a strong warming response. And finally, for this greenhouse gas, it is associated with long wave and leads to a warming over the ocean. So the summary here is that we found the atmospheric circulation lead to this North Atlantic warming hole in our slab ocean models. The change of the high-level westerly perturbs the cloud cover and affects the short wave and the long wave. But the most important is the surface westerly. It changes the LC temperature difference as well as the surface wind intensity, therefore leads to a cooling response. However, this cooling response is partly damped by the SSD itself, as well as the CO2 in the long wave. Therefore, overall, we have a warming hole in the slab ocean models. And finally, one discussion is, I mentioned before that the shape between the slab ocean model and the 40 carbon model are very different. We hypothesize it is because we don't have the Eichmann transport in our slab ocean model. We could offline calculate the Eichmann heat divergence in our slab ocean model. And we found so there is a heat divergence at the source of the warming hole. Therefore, we hypothesize if we have only Eichmann, so it may make the warming hole more closer to the observation as well as the 40 carbon model. Right now, we are actually re-simulating the historical climate change using the new ocean model hierarchy defined in 10L. So yeah, I think I'll stop here and I'm happy to take any questions here. Yeah, thanks.
Questions? Hello?
I'll go for Shannon's.
Oh, Shannon, go ahead. Ask your question.
Chengfei, great talk. In multivariate regression, if two of the factors are correlated with each other, sometimes it will make the attribution difficult to understand. So my question is whether you have checked those 6 variables are not correlated with each other before you do the multivariate regression.
This is a really good question. So yeah, basically this is the collinearity in the regressions. So we verified our linear regression with in the latent heat and the sensible heat, and the results are quite consistent with this linearization based on the Borg formula. So yeah, but we didn't check the time series for different variables here.
Okay, I see. Thank you.
Okay.
Hi, thank you. I've been looking at the warming hole in CESM2, and in CESM2, the direction of the wind trend is opposite. So it's a weakening instead of a strengthening of the wind trend in this region. So I was just wondering what you think about that. Is CESM2 just really weird, or do you think that this would maybe be different in a CESM2 slab model instead of CESM1?
Well, good question. So yeah, this is definitely interesting thing there. So yeah, I think the poleward shift of the westerly jet is quite robust among different models, at least in CMF5s. But I'm not sure in CFSM2 why it is like that. So seems to me it is kind of a weird thing there.
Thanks.
That's okay.
All right, thank you, Chengfei. Now we move on to our next talk. Will be given by Taylor Finn. Taylor?
You guys see the slides?
Yeah, that's good.
Great. Okay, so I'll go ahead and start. I'm Tyler, I'm a PhD student or PhD candidate at the University of Miami, working with Amy Clement. And today I'm going to talk about North Pacific climate variability in a new CESM ocean model hierarchy, which very conveniently Tian Yao just presented on a couple sessions ago. So these talks are all very related. His talk was great and covered the whole modeling framework we're using, so I definitely recommend checking that out if you didn't catch it. I'll skip over a lot of the stuff that he talked about, which is going to mostly be summed up with this. So Tian Yao covered this very well and extensively. So I'll go ahead and just move on from there. But basically, we have the four members that Tian Yao was describing, where you have the fully coupled model, the Ekman mixed layer, or the EMOM as we're calling it, the mixed layer, or the MLM, and then the slab ocean, or the SOM. So these are the four members we're working with. And here we wanted to kind of dive into what North Pacific climate variability looks like in this hierarchy. So just to begin, really simply, this is filtered SST variance over the North Pacific. In the top left here, this is the observed pattern, so you get a pretty standard Pacific decadal oscillation, or PDO-like shape. And then from here, this is the fully coupled. There's some kind of polar coastal signal here that may be ice-related, although it extends out into the KOE region too, so could be something more there. And then the three hierarchy members here also show the Ekman mixed layer shows a pretty similar PDO shape as well, but we don't really see this quite as much in the mixed layer or the slab ocean model. And so these percentages here are the correlations with the observed values here. So this is the 2D correlation, basically, how similar this map looks to this map. And so you can actually see that, surprisingly, the fully coupled is doing the worst with only 27%. And the Ekman mixed layer is doing by far the best at replicating the observed SST variance at about 60%. So this is just a really kind of broad look, and we'll dive into more of the specific North Pacific climate variability modes next. So the most common of these, the most well-known, is the Pacific decadal oscillation, which I mentioned on the last slide. So here I've shown this is the first EOF of North Pacific sea surface temperatures. So this top column, or this top row, shows the spatial patterns across the four hierarchy members. All of them look fairly similar if you look at their shape generally. I don't have them shown here, but their correlations with the observed values are all relatively high. The slab ocean actually has the highest, but it's not that much higher than the rest to really be kind of too notable or anything. And so the spatial patterns look fairly similar. The variance explained of the first EOF is all relatively similar, right around 35% for all of these. The time series, and do note that the time periods here are a little bit different, which is why this fully coupled time series looks different than the rest. But for the most part, these have fairly similar characteristics as well. So we're seeing, at least in the PDO, a lot of similarities across all of the hierarchy members. When we look at both sea surface temperature and sea level pressure linear regressions on the PDO time series, again, we're seeing kind of the same thing. We're seeing a bit more variability in how the sea level pressure response to the PDO varies across the members, but the sea surface temperatures are fairly similar. And with the power spectrum, kind of like we were talking about with the time series, these are all also very similar. So far, at least with the PDO, we're not seeing too much of a difference across the different hierarchy members. And I'll get into what that means at the end. So we're just going to go through a few other North Pacific modes and do kind of the same thing. This work is very much kind of in the exploratory stage. We're still working on a lot of this right now. So this next mode is the Victoria mode. It's also known as the North Pacific Gyre Oscillation. This is the second EOF of North Pacific SSTs. And again, you end up with a pretty similar kind of story as you had with the PDO. Although you start to see more of this variability, the spatial patterns change a bit. There's a general shape, but it's kind of morphing a bit across the hierarchy. You've got these one or two kind of relative maximums, and these seem to move around a bit depending on the member you're in. But that also could just be attributable to just noise. These aren't particularly long simulations. We have about 150, 200 years of data for each that we can use. But generally, again, there's nothing here that's really standing out as like, wow, this is really different across the members. And so with the linear regressions on the Victoria mode, you get, again, something similar as we saw with the PDO. All of them are relatively close enough to not really sound off any alarms or anything like that. And the same story with the power spectrum. So I think there's a pretty clear trend here with the sea surface temperature modes. We also have the sea level pressure modes, and this is where you start to see a lot of this signature really change. So this is the North Pacific Index, which generally is the atmospheric expression or counterpart of the Pacific Decadal Oscillation. So this is just the first EOF of North Pacific sea level pressure. So in the fully coupled, you see this pretty clear, simple gyre, just one spot, but it starts to kind of expand from its isolated spot just south of Alaska here to where it's now kind of spreading across the whole basin. So this is something that's interesting. We're not really sure. We don't have a good answer yet as to why or what exactly this means, but that's one of the areas we're working on now. So I'll skip through these just to save some time. But again, with these sea level pressure modes, it's again a fairly similar story actually with the SST regressions. Where you get, again, you're getting very similar patterns across all of the members. And then finally, we'll look at one more, which is the North Pacific Oscillation. Or I'm sorry, this NPO is the first EOF of sea level pressure. The other one is the NPI is the area mean. But this North Pacific Oscillation, the first EOF, is the atmospheric counterpart to the Victoria mode or North Pacific Gyre Oscillation. And these all look very, very similar. almost exactly the same, and they're all, the correlations with the observations are all very close to each other and quite high. So same story again with all of this. So I'll go ahead and move on to the takeaways. So as I've been saying, the leading sea surface temperature and sea level pressure modes in the North Pacific roughly look the same across all of these different ocean hierarchy members. So whether you have the seasonally varying mixed layer, which allows reemergence to appear, which is supposed to be one of the primary drivers of the PDO, or you have the Ekman wind stress included, it doesn't really seem to affect how the North Pacific variability is looking overall. And so one of the ways we're interpreting this is that it seems to suggest a more minor role or lesser role for ocean processes in the North Pacific variability than may have been previously thought within this CESM1 framework as well. And all of this is without historical forcing as well. Everything we've seen is just the pre-industrial control runs. Like Chungfei had mentioned in the last talk, we're running some historical simulations for this hierarchy, but we're still in the process of getting those simulations completed. And so I didn't want to share any of those results until that was done. So I think I'll end there and take any questions if there's time.
Any question in the room?
Nice talk, Tyler. I think you can hear me. Have you compared with observations? Is it correct to say that your fully coupled patterns are more similar to observations in all cases, or are there some where one of your other kind of hierarchical runs is more, I don't know?
Yeah, so that's a good question. The one of the four members, the one that actually ends up having the highest correlations with observations is the slab ocean. So that one consistently across all of the modes we saw has the highest correlation, but it's very modestly above the fully coupled. So it's like 0.7 to 0.65 or something like that. And we see that trend pretty clearly in all of them, where it's the slab ocean doing the best, then the fully coupled, and then the Ekman and mixed layer. Each of those two are a little bit below that, but they're all very, very close. Nothing to the point where it really stands out, I think. So yeah, that's a good question.
Sarah?
Yeah, I guess it's more of a comment than a question, but I was kind of interested in your NPI plots because I think of that sort of a proxy for Aleutian low variability.
Yes.
And to me, it's interesting that all of the sea level pressure anomaly patterns you pointed out are different, that the SST patterns still look so similar. So it's kind of interesting to me that sort of southward elongation of your, Aleutian low, essentially, that wouldn't impact the winds and then the air sea heat fluxes and then the SST. So I just thought that was kind of interesting that didn't seem to be the conclusion that you all drew from looking at the SST patterns that look so similar.
Yeah, that's a good point. And I think it's definitely still open to interpretation. Where the conclusions we made are we haven't written it up or anything yet, so I think you can kind of take that for what you will. And a lot of this we put kind of a big asterisk on because we want the historical simulations. We are pretty confident that those are going to give us a better, overall view of all of this. But unfortunately, the timing didn't work out to have those simulations ready.
I'm not sure if you
I think there's some discussion going on about the other.
There's one in the room.
Oh, okay.
I think one more question. Yeah, I guess I don't know if this this question would matter anyway, because I know this model has a poor tropical North Pacific relationship, but But given that, do you see any differences in ENSO with all these different configurations? Is that having
Yeah,
an
so
impact, or is it just that the tropics is so disconnected from the North Pacific in this model that it doesn't matter?
right. So in the only member that should have any kind of INSO variability is the fully coupled. The slab ocean obviously won't, and the mixed layer model won't.
It's not totally what the advisor said. I think there is some, at least there can be INSO variability in the slab, kind of a slab ocean in the tropics.
Yeah, so I think there can be, but I think theoretically there shouldn't be any, since the mechanisms
You
are
might
there.
want to
But
talk to Amy about that.
yes, yeah, I know she has a paper on the southern oscillation in the slab ocean. So yeah, but generally we're not supposed to be seeing INSO in much of these. So yeah, I don't know if that really helps too much, but I haven't looked at it specifically. I haven't looked at the INSO time series or anything, but yeah.
Okay, thank you. Let's move on to the next topic.
Okay,
Can you see my
Taylor,
slide?
you need to unshare your screen. Oh, okay, now it's good. It's not full screen mode yet.
Okay.
You need to share
I
it one more
show.
time.
Okay. Does it work now?
Yes, it's coming up. Yeah. Good now.
Okay. Well, thank you. So I'd like to talk about the CSM pencil ocean model. And as you can see from the large number of courses, this is a collaborative effort across the broad range of the groups. So what is the pencil ocean model? I would like to use the schematics of the ocean component in CSM to introduce what the pencil ocean model is, also called 1D pop and column ocean models or mixed layer ocean models in different literatures. So in the CSM model, we have a full ocean model pop, as you heard already multiple times. And then on the other end of the spectrum, we have the data ocean, which is prescribed SST and CIs. And you also heard a lot about slab ocean. So what we would like to do is adding one more hierarchy in between slab and full ocean called pencil ocean model. It's basically array of 1D ocean columns, so allowing the 1D vertical processes and their interaction locally, but does not allow any lateral processes in the ocean. So we can compare the full ocean case and the pencil ocean case and learn about the role of ocean lateral processes in climate variability and change. Or we can compare slab ocean and pencil ocean. We can explicitly diagnose the role of vertical mixing and mixed layer depths, entrainment, detrainment, and the reemergence. And this is nothing new, as you already heard from multiple excellent talks in this session already. There's been multiple studies using similar 1D ocean models. The series of papers listed here, including my 2011 paper, we used so-called Mike Alexander's mixed layer ocean model using Gasper mixed layer scheme. It calculates a prognostic mixed layer scheme, but the mixed layer scheme used in this mixed layer or 1D ocean model is not consistent with the corresponding full ocean model. So that was the limitation. We also heard about Tian Yao's nice talk. in his model, the mixed layer depth, spatial and temporal variability is prescribed. So it's not prognostically calculated during the model integration. There's another similar 1D model by UK Meadowfish group. They use the KPP parameterization underneath their Meadowfish unified atmospheric model. KPP is used in most of the ocean general circulation model these days, so it could be a nice setup, but they did not have full ocean model in this case. So what they want to do with the CSM2 pencil ocean model, we want to use the CSM2 ocean component, POP2, and just disable lateral processes so that our pencil model can be consistent with the ocean model as much as possible. Also, we wanted to use all these 1D models need flux correction, like the Q flux correction, the slab ocean model. In this case, we use the 3D flux correction for temperature and salinity, and we use the target climatology from the fully coupled simulation, so the runs can be consistently compared. Something new in the CSM ocean, pencil ocean model is we also apply the flux correction for the U and V in the ocean because the KPP needs the vertical shear. So we want to retain the realistic vertical shear for the KPP calculation, which was not done in the UK Meadowfish version. So this is governing equation for pencil ocean model. And the terms in black are all the 1D terms that's prognostically calculated while the model integration. The red terms we call G terms are the terms that's not represented explicitly in the 1D processes. So they are the lateral processes in the ocean. So what do we do about that? How do we prescribe that? So we need a two-step processes. The step one is to calculate the G terms. So we do the prognostic restoring. So we run some preliminary runs and get the target reference climatology. And at each time step, we nudge the temperature or salinity or velocity towards the target climatology. And we calculate the G term throughout the simulation. So in the particular example we are working on right now, we are using the CSM2 PI control, the climatology from years 400 to 2000 as our target climatology. And we call this step as a restoring one, and we ran 20 years of simulation. And what you get is the climatological mean annual cycle of the G terms. And we use that to prescribe in the second main run, so-called G term runs. So before talking about the G term runs, let me just briefly show you some details. So we learned over the course of this exercise, setting up the initial condition and the target climatology to be consistent is very important. For example, we are showing here the CSM2 PI control from year 400 to 2000. And you can see rather persistent trend in temperature and salinity in the global 3D mean sense. And we take the mean as a target climatology. So we choose the year 1161 as the initial condition, which has the restart file closest to the mean. And later I will show why it's important. Also, this is the G-term run climatology we backed out from the step one restoring simulation. So on the left, it's a temperature G-term, the right, it's a salinity G-term. You can see they're basically representing missing lateral processes. So the pattern looks like the the heat flux convergence and salinity flux convergence. In the salinity side, you can see bullseyes along the coast, especially where the river mouth is, because unlike the temperature, the dam actively damped by heat flux, the surface flux for the freshwater does not actively damp the salinity. So we have those bullseyes which need to be taken care of. So now we have G-terms. We can go to the step 2, and we can prescribe those climatological mean annual cycle of G-terms as fixed terms. So now they are not prognostically calculated. So it doesn't contribute to the inner annual variability of this 1D pencil model. And also we have additional SSS restoring because of those bullseyes I just talked about, you saw in the G-term. So we had test runs, couple of 100-year simulations in a exactly same configuration as the restoring one, with SSS restoring and the same initial condition. So these are 3 runs I'm going to talk about mainly, just to give you a reference. The run 10 is the 20-year restoring run. Run 11 and 12 are G-term runs with 2 different SSS restoring strengths. So we have 100-year simulation. So this is the 3D global mean temperature evolution. Let me walk you through a little bit. So there's 2 shading, green shadings. Dark shading is the one standard deviation range from the annual mean from CSM to PI control with the full ocean. The light shading is the maximum minimum range of a monthly mean from the same PI control simulation. And there's these blue greenish lines, which is very stable for 100 years. Those 2 are from run 11 and 12. So for 100 years, we got this stable simulation, global mean-wise. The other 2, the red and blue, that has strong warming trend, that has the incorrect initial condition at year 601, which is very different from the target climatology. And we can see how it can mess up the simulation. While the salinity temperature was stable, salinity drifted slightly over the 100 years. So we are still working on how to stabilize salinity over long term. So here's some regional result. So this is upper 200-meter annual average time series for the Labrador Sea. And we have temperature, salinity, mixed layer depth, and ice fraction. Basically, you can see they are within the range of the fully coupled ocean model annual mean range, which is the dark green range. What's interesting is that the mixed layer depth fluctuation is much smaller compared to the full 3D ocean model result. This could be due to the lack of lateral processes, but also there's some slight chance that maybe we are constraining mixed layer depths artificially too much. So we're still investigating how much this is just due to the missing lateral process. This is Southern Ocean plot. Now we see better strong salinity drift in this case, but the other variables are behaving okay for 100 years. So this was a quick introduction of the pencil ocean model in CSM. So implementation is ongoing. And we still have some outstanding issue, but we think we are close to completion of the implementation. And the goal is to have multi-century up to 1,000 years of PI control configuration, CESM2 coupled with pencil ocean model simulation made available through this working group. And also after that, we will add Ekman transport to the pencil ocean configuration. So hopefully in about a year, the hierarchy of ocean models available in CESM framework will be like this. Thank you.
Question?
Hi, Youngo. Thank you for the talk. I think you were answering my question just at the end here, but I'll just ask for further clarification. The current iteration of the pencil model doesn't deal with upwelling at all, correct? That's what the Ekman transport version is going to do?
That's correct, yes.
Okay.
Yeah.
So it's just the only vertical processes that it resolves is just mixing at this point?
Yes.
Okay, thanks.
I'm just curious, even though you have these drift issues, whether, in these 100-year simulations, have you looked at things yet, like the AMV, and I'm thinking in particular in comparing with Glenn's work?
Well, no, not yet. We are not fully comfortable to go into science yet,
Okay.
but hopefully soon.
Is there any online question?
I was just wondering how computationally expensive the pencil model is compared to the full model or the slab ocean.
So it's actually just a little bit of overhead to the atmosphere and the land component. So it's relatively cheap. Of course, the atmosphere takes most of the computational resources for full CSM2 anyway, but it's substantially cheaper than the full ocean.
Thank you.
Thanks.
Thank you.
Let's move on to the last talk of this session. It will be presented by Kay.
Okay. Okay, can you see my screen?
Yes, everything looks good.
Okay, thanks for joining, everybody. I'm Kay McMonagle. I'm a postdoc at NC State working with Sarah Larson right now, but I'm starting at University of Alaska Fairbanks in August. And I'm going to talk about changes to wind-driven ocean circulation and how they can amplify externally forced warming in CESM2. This is work that we did with Xining Hu and Ryan Kramer. So I want to start by showing this observed surface temperature warming pattern over 1979 to 2014. And what we can see, no surprise, is that the globe has warmed due to the increase in greenhouse gases plus some effect of aerosols and internal variability projecting onto the trend. And so we have some kind of warming pattern here that's been observed. And I kind of want to point out particularly that there's very little warming or maybe even a little bit of a cooling in the Southern Ocean and the East Tropical Pacific in the observations. We can look at something similar in the CESM2 large ensemble. So if we look at the ensemble mean or the externally forced component in CESM2, same time period, this is what we see. So clearly these two warming patterns are different, which maybe isn't too surprising because there is internal variability in the observations, and we've tried to remove that in the by taking the ensemble mean in CESM2. But we want to understand the warming pattern, what is setting this warming pattern, both in the real world and in the model. And understanding the pattern of the warming is really important because radiative feedbacks depend upon the pattern of the warming. This is commonly called the pattern effect. So in other words, if we have a different warming pattern, we're going to get a different globally averaged warming rate and a different rate of things like equilibrium climate sensitivity. So we know that the pattern of warming can be altered by ocean circulation changes. And there's also evidence that the ocean circulation has changed over the past several decades. So we think that ocean circulation could play some kind of role in this warming pattern. And we want to better understand how these changes to the ocean circulation have impacted both the pattern and the rate of global warming. And broadly, we could divide these ocean circulation changes into two different categories. So one is the Atlantic meridional overturning circulation, which we're going to think of as a buoyancy-driven circulation. And then the other is wind-driven ocean circulation. And so there have been quite a few studies showing that AMOC redistributes heat and the role of that on climate. And so there have been several studies that quantify how a change of AMOC would alter the rate of global warming. These tend to be kind of future climate projection type runs, so something like a doubling or a quadrupling of CO2. AMOC looks something like this. So there's warm waters moving northward through the Atlantic, deep water formation in the high latitude North Atlantic, and then cooler waters moving southward. So this is a net northward heat transport. In these climate projection runs, AMOC weakens. That then leads to a cooling of the high latitude North Atlantic, which increases the deep ocean heat uptake, and then that reduces the global surface warming rate. So what this looks like in one of those previous studies from Winton et al. 2013, they compare two models, one with fixed ocean currents and one with free ocean currents. And this is the SST trend in those models. And you can see in the free current scenario, the high latitude North Atlantic is much cooler. And that leads to a cooling overall. So in other words, projections of AMOC, where you have an AMOC weakening, show that that weakening of AMOC actually leads to less global warming. But if we're thinking back towards this kind of historical warming pattern, it's really debatable whether or not AMOC has changed in recent decades. And so we don't think that AMOC probably played a very big role over the historical period. Maybe it's more important for projections, but so far we haven't seen a large weakening of AMOC. So instead, what we looked at is the wind-driven ocean circulation. The wind-driven ocean circulation also redistributes heat. So I'm thinking things like the subpolar or the subtropical gyres here. And many of the observed ocean circulation changes seem likely to be wind-driven and therefore connected to atmospheric circulation changes. So in particular, I'm thinking of the strengthening and shifting of the southern hemisphere westerlies that's been seen in observations, and also the stronger Pacific trade winds, which you could also think of as a strengthening of the Walker circulation. So our scientific question was, how do externally forced changes to wind-driven ocean circulation alter the pattern of surface warming and the rate of global averaged surface warming? And our approach to look at this was to compare two historical CESM2 ensembles. So one ensemble that I'm going to call the fully coupled model, or FCM, has all of the changes, all of the physics that we think are relevant for the real world. So it contains these changes to wind-driven ocean circulation. And if we take the ensemble mean of that, we get the total externally forced signal. Our second ensemble has all of the same processes except for wind-driven ocean circulation changes. And I'm going to call this the mechanically decoupled model, or MDM. So if we take the ensemble mean there, we get the externally forced signal from everything except wind-driven ocean circulation changes. So if we take the difference of those two, what we're left with is the impact of wind-driven ocean circulation changes. And I'm going to focus on the time period of 1979 to 2014. A few more details about these ensembles. So these were forced by historical forcing with smoothed biomass burning. For the fully coupled model, we use 50 ensemble members. And for the mechanically decoupled model, we use 20 ensemble members, where the wind stress forcing on the ocean is fixed to a 6-hourly climatology from a pre-industrial run of the fully coupled model. So this is one way to visualize what's going on. So in each of the model ensembles, we have POP2, our ocean model, and CAM6, the atmosphere model, and these exchange different fluxes. So if we look first at the fully coupled model, CAM6 and POP2 are exchanging time-varying buoyancy fluxes and time-varying wind stress or momentum fluxes. In the mechanically decoupled model, that wind stress or momentum flux is just a climatology, and there's no deviations from that. Okay, so we want to focus on the wind-driven ocean circulation. So the first thing to check is to make sure that AMOC is pretty similar in this model, so that we can isolate everything except for AMOC in terms of the ocean trend. So this is showing AMOC max in a time series over the two models. So our thick lines are the ensemble means, red is the fully coupled, and blue is the mechanically decoupled. And the shading shows 2 standard deviations around those ensemble means. So in CESM2, there's an increase in AMOC through to about 1980, and then a decline after that. And over to the right is a histogram of the trend over 1979 to 2014 in all of the different ensemble members. So in both ensembles, the AMOC trends are similar, showing that the simulated AMOC decline is primarily due to changes in buoyancy, not winds. And that's what we would expect. Next, we can look at the trend in the wind-driven ocean circulation. So this is the ensemble mean of the fully coupled model minus the ensemble mean of the mechanically decoupled model. And I'm showing the barotropic stream function here. So reds are clockwise and blues are counterclockwise. And the stippling is where this is statistically different from 0. And so there's a lot of features on here, but the big things that we can see are a strengthening and shifting of the Antarctic circumpolar current, which is tied to changes in the Southern Hemisphere westerlies. And in general, these changes in the Southern Hemisphere westerlies in the model are consistent with the reanalysis wind trend. So we can find ensemble members that agree with the ERA 5 wind stress trend. And then we also see a weakening of the tropical and North Pacific circulations in the model, and that's tied to a weakening of the trade winds in CESM2. And this is inconsistent with the ERA 5 wind stress trend, so there aren't any ensemble members that are able to reproduce something that looks like the trend that we see in ERA 5. We can then ask what role that has in terms of the surface temperature trends. So this is the surface air temperature trend in the 2 model ensemble means, and both of them show warming nearly everywhere. There is a North Atlantic warming hole in both model ensemble means, and they're fairly similar in strength and in shape. If we take the difference now between these 2, we can see the role of wind-driven ocean circulation onto the externally forced warming. So that's what this looks like. So anywhere it's red here, wind-driven ocean circulation changes enhance warming, and where it's blue, wind-driven ocean circulation changes reduce warming. So we can see that particularly over the southern hemisphere, wind-driven ocean circulation changes enhance warming. And in the northern hemisphere, we have more areas of like red-blue dipoles, so some kind of shifting of the warming pattern. We can also look at this in a global average sense. Going back to highlighting our 2 regions that I talked about earlier, we can see that wind-driven ocean circulation seems to be enhancing warming in the East Tropical Pacific and in the Southern Ocean. Then if we look at what's happening to the global average warming rate, we can look at this over time. So the similar plot as the AMOC plot before. Our thick lines are the ensemble means, and I added on observations here as the black line. So we can see that our 2 model ensemble means warm at very similar rates until about the 1990s, and then you can see the lines begin to diverge, and that leads to a difference of 17% in the warming rate between 1979 and 2014 between these 2 models. Looking over at the histogram, this black line here is observations, and also interestingly, it looks like observations, if anything, maybe agree better with the mechanically decoupled model than the fully coupled model, even though the mechanically decoupled model is certainly the less realistic model. So we can think about why we see this amplified warming due to changes in the wind-driven ocean circulation. One thing that we could think leads to a different warming rate is ocean heat uptake. But the fully coupled model warms more than the mechanically decoupled model, and it also has greater ocean heat uptake. So the difference in ocean heat uptake cannot explain this difference of global average warming rate. So instead, what we think is happening is tied to this pattern effect. So this is the sea surface temperature trend due to changes in the wind-driven ocean circulation. And this amplified warming in the East Tropical Pacific has been shown in previous studies to lead to a reduction in low clouds, which can then increase the downward shortwave radiation towards Earth and enhance global warming. And so we think that's what we're seeing in the model. We see things that are consistent with this in terms of the top of atmosphere radiation as well as the cloud changes. So in conclusion, changes in the wind-driven ocean circulation alter the warming pattern and amplify the rate of global average surface warming by 17% over 1979 to 2014 in CESM2. Some implications of this, it's likely that the wind-driven ocean circulation changes in the real world have impacted the surface warming rate and pattern. Whether or not those are exactly the same as what's happened in CESM2 is probably not likely, but in the real world, we do expect something like this could be happening. And then also atmospheric circulation changes may be a significant source of bias in historical and future climate projections. So getting these wind stress trends right, as well as the ocean's response to them would be one way potentially to improve our climate projections. And so large scale, I think we really need to be adequately understanding and simulating the wind-driven ocean circulation to improve our climate projections. So in other words, AMOC is not the only part of ocean circulation that has these global climate feedbacks. And thank you. I'll take any questions.
Any questions?
Thanks, Kay. I appreciate the talk. Have you also looked at trends in SST variability between the two different runs? And is there a difference between the two if you have?
Trends in variability. We haven't looked at trends in variability. We do also have pre-industrial versions of the mechanically decoupled model. So we've looked some at like internal variability, but I haven't looked at trends in the variability.
Okay. Yeah, it would be interesting to know if variance changes in one versus the other.
Yeah, agreed.
Thank you. I think I am as a question too.
Great talk, Kay. I was noticing in your wind-driven ocean circulation map, you had the like meridional tripole in the North Pacific that you had the box around, but then also in the North Atlantic, and also in this plot, yeah, that like near like Cape Cod and Canada area. Is like, what is going on there? Is that like maybe like Gulf Stream related, or what do you think?
Yeah, that's a good question. I'm trying to take a deeper look into what's happening in the North Atlantic now, but I don't really have an answer for you. Something's happening.
Yeah.
Yeah.
Oh, very nice talk, Kay. I just wonder whether you can really disentangle wind and heat flux in the tropics. Have you looked at compare the SSTs or in the tropics? I just since it's wind is strongly coupled to heat flux in the tropics, can really separate those.
So the wind variability in the heat fluxes is still there. Back to that. I'm not totally sure if that's what you're asking, but so in our mechanically decoupled model, if the wind is stronger, that can still impact the heat fluxes. It's just the wind stress that is a climatology that's passed from the atmosphere to the ocean. Does that answer your question?
Yes.
Okay.
But I'm also curious. I was curious whether you can look at what happened in the decoupled runs in the SST in terms of SST tropics.
Like in the mean or trend, everything?
Mean or trend?
Yeah, we're looking into it. I mean, so yeah, in the trend, there's certainly the differences here. In the mean, there's also some differences, but in general, the mean state between the fully coupled model and the mechanically decoupled are fairly similar.
Thank you.
Any other question? If not, we are going to open for a discussion. Sarah, you're going to.
Do we have the slides from the update this morning? The very last slide had some discussion questions on it. Otherwise, I can share my screen with it. So as this gets queued up, I can sort of elaborate on the motivation for this previous session was, again, conversations with many individuals in attendance, and also Amy Clement, who couldn't be here. And we were talking about how there seems to be a lot of, development sort of in parallel by different groups across, our community about, these different either idealized ocean runs or sort of switching on and off different capabilities, like as Kay was describing, the wind-driven ocean variability. And I've seen some other groups, kind of playing around with the air-sea heat fluxes. Of course, there's ocean-only runs that do these kind of things too. And so we were starting to realize that there's been a lot of development effort, particularly with groups using CESM, and now even CESM2. And so what we were kind of hoping to do is have a little bit of discussion, and I don't know if this will take much time, to sort of get a sense of where we're at and where we'd like to go as a community in terms of like building capabilities. Would we rather share data or share codes? Like, what's the easiest thing? And then ultimately to potentially gauge interest either from individuals or the whole group as a whole about whether sort of a greater, workshop sort of focused on what groups are doing and sort of big picture where we think we should go as a group in this ocean hierarchy question posed as like a greater workshop. So I guess it's a little hard for me to know what's going on in the room. So I guess Aishu and Isla, I'll sort of lean on you guys in there. But, based on what we've seen, there's the stochastic model, the mixed layer model with the seasonally varying mixed layer depth, the slab, adding in the Ekman capabilities, Kay's version where he's going from a fully coupled model and removing complexity. Apart from those, sort of what gaps do we think we see in the current hierarchy, and what would we like to see moving forward? And I'll just open it up to anyone, really.
Now, this is Isla, I guess. I don't really work in this area, but I feel like one thing I learned from all of these talks is that it's very easy to get the right answer for the wrong reasons in some cases, or get the wrong answer because you're just missing something like the AMOC. And so I'm wondering is there some kind of like standard practice for, or some kind of, best practices for ensuring that what you're seeing is reasonable. I think it was Chang Fei did that very nice analysis in the model of all the different fluxes and what's contributing. I mean, is like comparing that as best we can with observations the way to go, or is it not that simple?
Yeah, I mean, that's a really good question. And I think in addition to, some of these models have an AMOC and some don't, I think Matt Newman brought up that INSO is different. So things like the slab ocean have like this thermodynamic kind of INSO-like feature, but it's different. But fully coupled has INSO, and how does that sort of project onto what we're looking at too, I think is a big question. And being aware of that when we do these comparisons is really important. But I don't think there are best practices. I think we're still figuring out what everyone's doing and understanding everyone's development efforts.
I mean, it seems like having this broader hierarchy is going to help, that we can start to see across the hierarchy where we get things wrong, right for the wrong reasons, or we're adding in a different process helps a lot.
Yeah, I have a comment is maybe right now, although for this hierarchy, we're trying to simplify the ocean model. And for CMF6, there's another set of simulation called FOFMAP, the flux anomaly forcing experiment. In those experiments, we basically try to isolate what is the temperature and the circulation change caused by the external faulting, how that will contribute to local and global changes in the climate. That one, we just need to build some other capability into the 3D model to isolate those processes while the model is running. Maybe this is another way to isolate the physical processes than just simply simplify the ocean model.
Yeah, other thoughts on what we're missing? Sheneng, I see your hands up.
Yeah, I just want to quickly share my thought on this. So it seems to me that there are currently two parallel pathways to build the model hierarchy. So one is making the slab ocean model more and more complicated, and the other is making the fully coupled model more simpler and simpler. So I'm not sure whether those two pathways will at some point converge or not, because technically these are very different approaches. So for example, the slab ocean model always confuses me in the sense that in that model, ocean circulation is not fixed, but rather it's the ocean heat transport is fixed, right? So if we think about under climate change using the slab ocean model, so we are saying that let's first of all assume the ocean heat transport doesn't change. So what the global climate would look like. So this is what slab ocean tells you. So then on top of this slab ocean model, we start to add in the components like the Ekman transport, for example. So in that way, we are adding back the oceanic processes like the ocean circulation. So it seems to me that those two approaches do not fit each other, because one is focusing on ocean heat transport, the other is ocean circulation. But maybe it's just me that haven't fully understood this approach yet. So I just want to hear the thoughts from the audience, how you think of those two approaches. So it seems that it's only me that's confused.
I guess I can share a little bit of my thought, because I think what you're saying is top down versus bottom up kind of development. And I think I developed that Ekman mixed layer model, but on top of everyone else. But but I think that's more like a bottom up process. And the bottom process, I think the pros is that you always understand what you're exactly doing, because all the processes you just name it, and when you name it, you actually, if you're able to name a process, that means you're able to quantify it, right? Like, but when I was developing that, I realized that, say, how is it possible to decouple Ekman and the geostrophic flow? Because I mean, physically they're actually the same thing. Like, you actually have you first need to have the Ekman, and you build up the SSH, then reversely it builds up the geostrophic flow. So in the way, they're not separable. Actually, they're actually not really separable. So I think a lot of time it comes to how you interpret your simplification. So what I came across is the problem is about interpretation. If you go from bottom up, and that's where kind of I find the top down, the beauty of top down, because the beauty of top down is it's already complicated enough. So when you usually you simplify things to turning on and off certain knob that already exist. So I think that's kind of the thing that top down can do easily, whereas bottom up, you sometimes build in a way they're not exactly consistent. Like I think another thing I came across is that what is Ekman thickness? Like, does Ekman layer coincide with the mixed layer depth?
Yeah.
Right, and that is not really a thing when you use the simplified model. But if you want to connect to the say the OGCM, and the OGCM just let the model resolve itself. They don't necessarily define such a layer. So I think that's where that's probably kind of that falls into the same category of the question you just proposed. Yeah, I don't have a good answer, but I know where they disagree. It's not even disagree because they start with very different kind of direction. So there's no point they agree or disagree because they build on top of very different idea. I eventually I think it's still very problem dependent, but it's necessary to kind of think about this when anyone wants to study a problem using a hierarchy. It's like your interpretation is very important to decide which approach you want to use.
Yeah, I fully agree. Yeah.
I think to me, for the slab ocean model, basically what you want to test is if the ocean mean state does not change, what kind of climate or climate change you can see. And afterwards, when you add Ekman or add this tensor model, you try to put some of the ocean variability into your equation. And for 3D model, you not only have the ocean mean state, it also has this ocean variability. And if, like with the slab ocean model, you can see something close to the observation. That means with the mean state of the ocean, you pretty much can reproduce a lot of things. And a lot of things as observed. But if you don't have the ocean mean state, maybe you will not be able to see whatever you have seen successfully from the slab ocean model. That means using slab ocean model, once you reach any conclusion, you need to be careful about, you have built in those ocean mean state, or you use a Q flux.
I think we should have a break before the next session.
Okay. If there's not any other question, we just take a break. Maybe
Can I
we
just say
come.
one more thing real quick?
Okay, sure.
Sorry, it's not really a question, it's more of a comment. This might be heretical to say at a CSM working group meeting, but I'm wondering, does anybody happen to know if any efforts are being made at places like GFDL to do something similar? Just noticing the differences between CSM1 and CSM2, I'm worried that we're going to learn a lot of useful things in CSM2 that are going to be very model dependent. And I'm just wondering if it's worth the effort of bringing along other modeling centers while you're developing an ocean model hierarchy so that we can look across models as well as within models.
Yeah, Dylan, I assume that's Dylan.
Yeah, it is. Yeah.
I think you're really hitting on sort of the motivation for like the question 4, which would be, bringing not just CESM model users, but getting more of the community involved to get a better sense of like model dependence. I know there is some version of the GFDL model where they, force the ocean with climatological wind stress, and I think you Zhang's papers. So there is some stuff I know from the top-down approach, but I don't know about the bottom-up. And so it sounds like if we did try to move forward, because it sounds like there are a lot of pretty big questions that we all need to kind of get in a room together and figure out, where we're going to meet in the middle, or if it's all just going to be science question based, how we decide to develop these things. But it does sound like we need other modeling groups, part of this too.
Right. Thank you.
Okay, let's conclude this section, and let's take a 10-minute break and then come back at 3:05.
That's okay.
how to stop share.
Can you see my screen now?
Yeah.
Is it working?
Yes, everything looks good.
Good. Excellent. Let's start. Good afternoon, everyone. I'm Jerry Shi. I'm from Woods-Hole Oceanographic Institution. I'm a postdoc working with Yang O and Susan Weifel. I'm very excited to show some result about our recent publication, which is about subsurface ocean temperature responses to the anthropogenic aerosol forcing. So first of all, I would like to talk about some background information associated with the climate effects of anthropogenic aerosols and also from the greenhouse gases. So as we know, the anthropogenic aerosols and greenhouse gases are two leading forcing agents leads to substantial changes in our global climate. So here I'm showing an example about this climate effect for the sea surface temperature trends from the simplified multimodal mean. As we can see in the left top one, the greenhouse gas can give rise to a global warming from the single forcing run. And on the top right one, it is a result from the aerosol single forcing runs. We can see cooling, especially distributed in the northern hemisphere. As if we compare these two panels with the bottom one, historic one, we can clearly see the compensation between these two forcings on the sea surface temperature change. And similarly, on the right-hand side, I'm showing the sea surface temperature trends from the CESM1 large ensemble. This one is from Clara Desert's paper in 2020. And they have shown the long-term trend, 50-year trend during different periods. And they have found the aerosol, anthropogenic aerosols and greenhouse gas are leading forcing agents during different periods. For example, the aerosol plays a dominant role before the late 1970s, but after that, greenhouse gas play a leading role. And based on this plot, we can see the aerosol can give rise to a very strong cooling signal in the North Pacific, especially after the 1950s. And a lot of previous studies have focused on the surface and atmospheric responses to the anthropogenic aerosol forcing, including the surface temperature I have mentioned in the previous slide, and also the ITCZ shift associated with the hemispheric energy imbalance, and also the sea level pressure changes, such as the changes of alluvial load. And here, importantly, we found that the aerosol forcing can also give rise to substantial changes within the ocean. So here I'm showing the example about that. This is the AMOC responses to different external forcings, such as the aerosol single forcing and also the greenhouse gas forcing. And we can see a strong effects of anthropogenic aerosols on the AMOC anomalies. However, in this talk, I'm not going to talk about the changes in the Atlantic basin. I will focus on the subsurface temperature changes in the North Pacific, because we can find a very strong signal in the North Pacific. So to show this point clearly, I'm showing this plot about the UF patterns of sea surface temperature from the CESM1 aerosol forcing ensemble. So here I'm showing the first two UF modes, and all of these ensemble members are concatenated in time. As we can see, the first mode, the time series is quite noisy, and the spatial pattern is associated with the IPO, seems to reflect the internal variability. In the second mode, we can find a tremendous cooling signal in the North Pacific, and this one is likely to reflect the effect from the aerosol forcing. And based on the time series, we can see it increased before the 1980s and decreased in future scenarios. So it seems North Pacific could be a good place for us to find the aerosol signals within the ocean. However, if we also look at the UF1, the Pacific also is rich of a lot of strong internal variabilities and is complex. So another question is whether the fingerprint driven by the anthropogenic aerosols identifiable from the background noise, such as internal variability. And we found the large ensemble simulations are important and very helpful to answer these questions. So next, I will show the two models with large ensemble simulations used in this study. The first model we use is the CESM1 large ensemble simulation. The first set of large ensemble is the all forcing runs. It is widely used with 40 members, identical radial forcing, and different initial conditions. And another set is CESM1 all but one forcing runs. So it is same with this all forcing runs, but without the industrial aerosol forcing with 20 members. So we can use this equation to, we can use this equation to derive the anthropogenic aerosol single forcing ensemble. So to test whether our result is robust across models, we also look at the result from the Canadian model, the Canadian ESM5. It is also a large ensemble simulation. So in this model, the model design about this single forcing is a little bit different. So the aerosols are the only time varying forcing agents. And this large ensemble includes 15 members. So although they have different experimental design about this single forcing of aerosol, I will show you later that the results from these two models are quite consistent in terms of the aerosol-induced responses. And the region we focused on is the upper 1,000 meter temperature change in the non-specific, and the period we are looking at is from 1950s to 2014. And furthermore, we use a signal-to-noise maximizing pattern analysis to find the pattern that maximize the signal-to-noise ratio. So in this method, these extracted patterns are associated with the maximization of the ratio of signal, which means the variance of the ensemble mean to the total variance from all the ensemble members. And previous studies, such as the paper from Rod Wills, have found this method is very useful for us to extract the false response, especially given the limited ensemble member. And below that, I'm showing the result, the first two modes based on this pattern recognition method. And these two modes, the signal-to-noise ratio in these two modes are higher than 1. It seems to indicate these two modes are associated with the false response from this CESM1 aerosol single forcing ensemble. And for the first forced mode, we can see there is a broad cooling in the non-specific, and the corresponding time series for that is quite linear. So we can regard this mode as a linear mode induced by the aerosol forcing. And the second mode is more interesting. It has a very unique zonal mean pattern in the non-specific. For example, there is a broad cooling at the surface with a polarward intensification, especially in the subpolar regions. And we can also find the cooling signals penetrate into the interior ocean via the ventilated thermocline. And to the south of that, on the equatorward flank of the subtropical gyres, we can find a warming spot right here. And the corresponding time series for the second mode, forced mode, is nonlinear or non-monotonic. It increased first until the 1980s, and after that, there is a decrease for this time of evolution. And we can compare these results from CESM1 with the result from the Canadian model. And again, the first mode and the second mode. Surprisingly, the first mode, there are quite some discrepancies between these two models, especially the magnitude of these cooling signals. However, the time series seems to telling the same thing. These first modes both represent the linear mode. And in the second mode, for the Canadian model, we can also find some regional differences between this model. but they are broadly consistent, especially associated with the structure of this warming pattern. And there is also a good agreement in this time evolution. So in the next step, we will focus on the second force mode, which is associated with the nonlinear effect, non-monotonic effect of the aerosol forcing. And the first mode is quite linear. It seems this mode will be partly compensated or even overwhelmed by the greenhouse gas warming effect, which is also linear. So it seems it is possible for us to detect this nonlinear, non-monotonic effect in reality. And then we can do some regression analysis on this time series from the second mode. So here I'm showing the regression pattern of aerosol optical depths on this time series. So we can use this to find the primary sources of aerosol forcing. As we can see, most of these sources came from North America and Europe. It seems to, so this time series, it seems to indicate the aerosol emission due to the industrial development, and after that, the decrease seems to associate with emission regulation in these two regions. And we can also find these the aerosol sources located mainly to the north of 30° north. That seems to be why we can find a polarward intensification of surface cooling. And then I will talk about some result based on 3 observation datasets. The first 2 observation datasets are from the EN4 from the Hadley Center. And here we pick up 2 versions which are different in their how they correct the biases associated with XBT and MBT measurements. And the third dataset we use is the IAP dataset, which is from the Institute of Atmospheric Physics. And we did a similar analysis as we did on the large ensemble simulations, the pattern recognition analysis. But there is a little bit difference how we regard the noise in this method. So in the simulations we mentioned earlier, we regard the noise as internal variabilities because they have plenty of noises associated with internal variability. And in reality, these observation datasets, they have identical force response and the identical internal variability. So the noise we analyze in this method is uncertainty due to the method they produce these datasets, such as the gap filling method and the correction of the biases of XPT. And here on the left-hand side, I'm showing the result based on these 3 datasets. So all of these results are detrended before the pattern recognition. As we can see for the first extracted pattern right here, we can find a broad warming at the surface, and this warming penetrate into the interior ocean following the thermocline. And we can, to the south of that, we can also find a negative change of subsurface temperature on the southern flank of this subtropical gyre. And for the time series for this first extracted pattern, it is also nonlinear. The pink curve is annual mean, and the red curve represents the 5-year annual mean. And for the second mode, the extracted pattern, we can see has a triple pattern right here. And then we got the patterns from the observations. We can compare these patterns with the ones we have shown earlier, such as the forced pattern 2 from the aerosol single forcing runs like this. And in addition, we also show the pattern associated with the internal variability. For example, we are showing the PDO-related pattern, which is derived from the pre-industrial control run. So we can clearly see the difference between the signal and the noise associated with the internal variability. So in the next step, we calculate the pattern correlation between the observed and simulated pattern. For example, the left in the first table, I'm calculating the pattern correlation between these extracted pattern from observations with this forced pattern 2. As we can see, the EP1 matches pretty well with this forced pattern 2 from the aerosol single forcing experiment, which are much larger than the correlations from the other extracted pattern. And the second table, I'm showing the pattern correlation between the observed patterns and the PDO-related pattern from the pre-industrial control run. And the EP2 matches well for this PDO-related pattern. It seems this first node is likely to reflect the aerosol effects with a clear non-monotonic feature. And the second node right here seems to reflect the internal variability. So here I have some takeaway points. So first of all, the aspergatic aerosols do leave their fingerprints within the ocean, and it has a characteristic spatial pattern and non-monotonic feature of aerosol effects, which can be extracted from the strong background noise. And these temporal and spatial information are very useful for us to understand the recent observed changes and also improve future projections. So I will stop here. I'm glad if you have any questions. Thank you.
All right, we just take one quick question, and Shenghui, you can ask the question.
Hi, Jerry. So thanks for the nice talk here. So I have two questions, actually. The first one is about your first figure. So you showed that the greenhouse gas actually leads to a strong temperature gradient between the northern hemisphere and the southern hemisphere. And at the same time, in the greenhouse gas run, the AMOX is actually reducing. So my question is, so what kind of mechanism lead to this strong gradient between the two hemispheres for the SST? And the second one is that, so why the aerosol fingerprint is in the North Pacific rather than in the North Atlantic? Because North Atlantic is much more closer to its emission regions. So yeah.
Yeah, for the first question, you mentioned that there is a hemispheric symmetry in the sea surface temperature induced by greenhouse gas. Is that right?
Yes.
It seems not that clear, but for the aerosol effects, the hemispheric symmetry is much more clear because the sources of aerosol forcing is mainly distributed in the northern hemisphere. But for the greenhouse gas, it is well mixed. So it's hard to say there is a clear asymmetry in the sea surface temperature change, sea surface temperature change induced by greenhouse gas. And is that good to answer your first question? Because I'm mainly focused on the aerosol effects, not the greenhouse gas effects in this talk. So
yeah,
for your next question about aerosol, can you repeat that again?
So my question is why the fingerprint is likely mostly in the North Pacific rather than just in the North Atlantic.
So the possible reason is the location of these sources. So it's right, there is an open ocean, wide open ocean in the North Pacific, but for the North Atlantic basin is smaller, and we can find there is also not a warming hole, as you mentioned, or the aerosol can induce a cooling hole. It's warming. So it may affect, we cannot find a very strong negative change of temperature at the surface induced by aerosols. That is maybe my guess. I'm not sure whether that is a good answer for that.
Yeah, thank you. Thanks.
Move on to the next talk. Next talk will be given by Kevin Chambers.
Yeah,
okay.
This is Kevin. Can you hear me?
Yes. It's kind of low.
Hello?
Yeah, that's good.
Yeah, well, NCAR won't allow me to share my screen, and so somewhere you've got my presentation there, I hope, and it's all degraded. Unfortunately, it has a lot of actions on it, so I'll just have to say next. Can you pull up the presentation, please? Also, I'm a bit light here on modeling. This is mainly observations. but that's one of the deficiencies of a lot of the work that goes on, is there's very little regard for observations. I was pleased to see some talk of observations in the last presentation. Can you start my presentation, please?
Right.
So,
can you see the screen, Kevin?
So, where's the presentation?
Hold on.
All right, next. Next. So, you know, conventionally, we look at the at global warming through the global mean surface temperature record. Next. And the relationship with carbon dioxide. So this is the up-to-date record through 2022. Next. And it's quite noisy. Next. And so here what I'm showing is the ocean heat content down to 2,000 meters on the bottom and the global mean surface temperature at the top. And you can see that the ocean heat content is a much more reliable indicator that global warming is actually happening. Some of the fluctuations from year to year in the ocean heat content are real. Some of them are probably in the noise level, but the relentless increases are certainly real. Next. And so this is the observational base for the various records from GFDL or from the IAP record, which is mainly what I've been using. And you can see on the right-hand side the changes over time, and it's only after about 2006 that you can really go down to 2,000 meters. But by using that record, we've been able to reconstruct the record reliably back to about 1958. Next. And so this is not quite up to date, but here's the overall record up above. And what I wanted to show here is the record of warming as stripes for the 500-meter layers from the surface down to 2,000 meters. And so that you can see the warming in the top 500 meters showing up in the late 1970s. And then in the 500 to 1,000 meter layer, somewhere around 1990. And then in the below 1,000 meters, 1,000 to 1,500, the late 1990s. And then after about 2005, down below 1,500 meters. Next. And so this heat penetration, there we have it, about 2,000 meters in 30 years. And this is a challenge for models. The studies we've done looking at the data suggest that the models have incorrect stratification in the top layers, and they have too much heat penetrating with depth. And so there's a lot more use of the observations that are needed in order to validate models. Next. Next. So this is the record up to date through 2022, and there's the 2022 anomaly in the lower left down to 2,000 meters. Next. And this is down to 100 meters. You can see some similarity, but you can see the La Nina signature much more pronounced in the top 100 meters. You can see it also to some extent down to 2,000 meters. Next. And so, you know, here's the La Nina, a good part of the La Nina signature. And you can see the warmth in the Western Pacific and especially down in the Coral Sea. And of course, that's the next El Nino that's coming. Next. And in the very pronounced warming in the North Pacific and throughout the South Pacific, and especially around where I am now in New Zealand, is a signature of the La Nina. Next. And then the Atlantic as a whole is warming up, but it's showing up especially in the South Atlantic. Next. And so next, yeah. And so if we look at this region here, you can see this is below the surface as to what's happening pretty much up to date, and you can see the penetration of this the warmth along the equator out into the Central Pacific. But there's this huge volume of warm water in the Coral Sea just south of the equator that is surely going to play a strong role as we move on. Next. And also going along with this are large changes in salinity. This is the up-to-date values for 2022 on the top for the salinity, and down below is the climatology. And the North Atlantic is in 2022 got a lot saltier. The South Atlantic did a little as well, and that doesn't match quite as much with the climatology down below, but you can see there is a resemblance between these two. And so in general, this pattern, which we've shown for the general trends in salinity in the ocean, is that the salty areas are getting saltier and the fresher areas are getting fresher, which means that the wet areas are getting wetter and the dry areas are getting drier. And so this is a key part of the signature. And of course, that extends over land. So the dry areas, the drought areas are more prone, and the wet areas are flooding, but that does depend upon connections to water sources. Next. This is the sort of regional breakdown, and there's some unusual profiles here in the Indian Ocean and the North Pacific, Mediterranean Sea, relatively abrupt increases after about 1990 or 2000, much steadier, larger increases in the Southern Ocean and in the Atlantic as a whole. So that's where the strongest warming is. And of course, this is very much related to the role of ENSO in the Pacific as to keeping the overall Pacific cooler as a consequence. Next. And so there are these hotspots that develop as a part of the overall global warming. Sometimes if they last long enough, they're called marine heat waves, but many of them tend to self-destruct because they attract activity in the atmosphere, and then they lose heat through evaporative cooling, and they fuel the storms. And so this is what is giving rise to all of the increases in extremes in the weather and climate around the world. Next. So a few examples I'll just mention here: the California floods. Next. The Pakistan floods last year, and many Australian floods, rather eventful, which is typical, of course, of La Nina in Australia. Next. And we've been bombarded here in New Zealand. I want to show you a little bit of that just recently. And next, just recently, there was 2 days ago, there was 23 inches of rain in the Sao Paulo area of Brazil in 24 hours. Just incredible flooding with rain bombs. So next. And so in Pakistan, there was record heat in March through May of 2022. And there's a lot of information on this slide, which I don't have time to dwell on, but you can see especially hot in the Indus River floodplain region. And then next, this is March through May, and then July, August, the Indus floodplain was bombarded with rainfall, and there was extensive flooding with over 1,700 dead, and the crops were devastated, and that's still in that state today. And this includes things like cotton, the livelihood of the farmers in Pakistan, wiped out by this, but very much related to the warm Indian Ocean, Northern Indian Ocean, that was related to the heat that we saw in March through May earlier. Next. I'm just showing one slide. This was a rain bomb that occurred in Eastern Australia in March of 2022, which led to huge amounts of flooding and 790 millimeters of rain in a week, and over 20 deaths. A lot of this was relatively local, but still devastating. Next. And here's some scenes from the atmospheric rivers that we're feeding off of the warm sea temperatures, ocean temperatures in the North Pacific, coming into California. Next. And then where I am, you can see in the second slide where my location is. We had 280 millimeters of rain in a day. That's 11 inches. And the city of Auckland, a little further south, had over 10 inches. And all through there, all of those red spots had very extensive rains, very much related to this La Nina pattern. And it's essentially a rain bomb that came down as a subtropical low pressure system and led to remarkable flooding. You can see Auckland International Airport internally as well as externally was flooded. And major highways were flooded, and so on. Next. And then we had tropical cyclone Gabrielle came down and hit us right where I'm located. You can see the sea level pressure map down the bottom, 968 millibars of pressure was recorded right near where I am. And this is a hybrid system now, and caused extensive flooding and damage. The rain in our area on this occasion was about 100 millimeters. Next. And so there's the actual rain trace there in this case, right where we are. And so this is again a consequence of the very warm ocean temperatures initially in the Coral Sea and throughout the southwestern Pacific in particular, as a consequence, was one of these hotspots of marine heat waves associated with the ocean warming. Next. Well, here's some of the damage that occurred. I mean, there's still over 1,000 people missing in New Zealand. There are huge areas that are just completely covered with silt and slides. Houses and cars have been buried, and many areas are cut off, and they're also cut off from even cell phone coverage. So there's a lot of recovery work going on right now, and we don't know what the death toll is. Next. And so ocean warming is continuing. Ocean heat content is going up, but we get these hot spots, marine heat waves. Some of them are transient, but overall the ocean is warming. Over 90% of the heat from global warming goes into the ocean. And one of the consequences is that we have a lot of activity in the atmosphere, especially with the extra water vapor that leads to flooding. And there's a tremendous amount of evidence for that. And the question is, how well is all of this kind of stuff simulated in models? Next. This is my contact information. You can reach me through my NCAR email. And next, the final slide shows you my book, which tells you about why all of this is happening. Thanks.
One quick question.
Yes, I have actually a question for Kevin. Thank you so much, Kevin. Very nice presentation. Nice to see this well, nice. I mean, it's worrisome, but nice to see your analysis of the subsurface heat content. So a quick question I have is, you seem to be relating this extreme floods in Eastern Australia and New Zealand to this increased heat. To what extent do you think they are due to this prolonged La Nina that we have seen during the past few years?
Well, yes, that's obviously played a role. And the thing is, the first year of a La Nina inherits the sea temperatures in the extratropics from the previous El Nino, and they're quite different in the extratropics. And over time, we get this buildup of heat in the North Pacific and in the South Pacific. And so the second year of the La Nina is rather different than the first, and the third year compounds it even further. And so this buildup of heat, especially in the Coral Sea and all around the Tasman Sea and the New Zealand area, is very much a part of the La Nina signature. And the prolonged nature of it has meant that this has got not just a surface signature, but quite a substantial signature below the surface. So that I think in New Zealand we've had 6 or 7 of these subtropical storms. We would normally call them cut-off lows. We have blocking highs at higher latitudes, and these cut-off lows come down, and you know, occasionally, as in this case with Gabrielle, it was actually a hurricane that they call it a cyclone in this area that became a hybrid storm. And so it had some baroclinic aspects to it as well that was a fairly rare event, but it's caused a tremendous amount of damage as a consequence. So I think it's a combination of global warming and the La Nina.
Yes. Sounds good. Thank you.
Thank you, Kevin. Next talk will be given by Pedro. Pedro, you're muted.
Yeah, sorry. I'm going to share my screen. It should work. Can you see my slides?
Yes.
Awesome. Like everyone else, I'm interested on understanding why the Pacific is cooling while the rest of the planet is warming. So a few months ago, I had this intuition and it was simply an intuition. I could tell you more how I thought about it, but that it somewhat involved having higher resolution simulation of ocean processes in the Southern Ocean to produce the right amount of cooling in the Southern Ocean. We know this has been a very active area of research, and we know that if the Southern Ocean cools, then that signal can be propagated into the tropics, and through feedbacks can be with the tropics, it could be amplified. But how do we produce enough Southern Ocean cooling in a model? So here I'm using, I'm going to be showing results from a comparison of high resolution versus standard resolution simulations performed with CESM1. The high resolution ones were part of the IHES project coordinated by Ping Chang. And the standard resolution is the now super famous CESM1 large ensemble. The higher, everyone is familiar, I'm sure, here with the standard resolution of the large ensemble. The higher resolution runs are also with CAM5 in the atmosphere, but a 1/4 of a degree, and with POP2, but at a 1/10 of a degree, which is eddy resolving, eddy permitting. These runs with the high resolution CSM were run under historical and RCP 8.5 forcing from 1920 to 2100, very much like in the large ensemble. There's 40 members of the large ensemble. I'm going to be looking at 3 runs using the high resolution CSM. These are extremely expensive simulations. So this is all that we have, and I'm going to be trying to show you some insights based on only 3 runs. I'll be focusing on 2 analysis intervals. one spanning the entire 21st century where forcing dominates. So I can use these 3 runs to isolate externally forced signals and compare them with the large ensemble. And then I'm also going to take a look at the last 40 years, 1980 to 2021, which is the period in which the Pacific has been cooling and the Southern Ocean has been cooling. All right, so first results. First things first. If we look at the changes between 2001 and 2001 and 2100, so the entire 21st century in sea surface temperatures in these 3 runs, which I'm calling round 1, 2, and 3 from the CSM high resolution, you're going to see that the model simulates almost absolute cooling over a vast area of the Southern Ocean in the Pacific sector. And there's cooling elsewhere in the Southern Ocean. I'm focusing on the Pacific sector because it's where the cooling has an influence on the Pacific. And these 3 plots show us that the changes are very robust to internal variability, and they're largely an externally forced response to increasing greenhouse gases, which is the dominant forcing over this interval. We can compare with the ensemble mean. So I'm going to take a naive 3-member ensemble mean over this interval. So these are linear trends, least squares, linear trends, and I'm plotting the change over, represented by this trend over this 100-year interval, which you can see in the color scale. And I'm also plotting the same the changes over the same interval computed in the same way from the CSM1 large ensemble to the left. And you can see that many of the patterns are similar, but we see a lot less cooling over the Southern Ocean. Actually, you can compute the difference, and that's what I'm showing on the right, but you don't have to compute the difference to see that the high resolution version of CSM produces actual cooling in response to greenhouse gas forcing, whereas the lens produce less warming, but nowhere in the Southern Ocean there was cooling. So it's a much stronger response or relative cooling, depending how you want to see it, in many of these areas in excess of 2 degrees different between what the lens does and what the high resolution 3-member ensemble mean shows. So we can ask ourselves, can this response explain the cooling over the past 40 years? Well, things get a bit more complicated because internal variability starts to play a role. So we can do the same thing, do my naive 3-member ensemble mean to the right, and the 40-member mean from the lens, which we trust is capturing the externally forced response. And we can see that the lens produces a pattern of enhanced equatorial warming that a lot of us have described in the past. Less warming in the Southern Ocean, but no signs of actual cooling like observed. Our 3-member mean shows trends that resemble more what we have observed, but these are only 3 members. So let's take a look at each individual member. And here you can start seeing differences, and the differences are attributable to internal variability, which can be strong in the Pacific over 40-year periods, like the one shown here. But you can also see that there's some patterns that are similar, particularly the strong cooling in the Southern Ocean. So is this higher resolution version of CSM doing something structurally different? Well, we can look at the lens and see if there are runs that look like my 3 runs from IHESP. So here on this top row, you have the trends over the last 40 years simulated by CSM high resolution. And I identify through pattern correlation over the Southern Hemisphere in the Pacific. I identify 3 runs from the lens that resemble the trends simulated by IHESP. And you can see that despite IHESP simulating stronger cooling in the Southern Ocean, it's not as strong as observed. The bigger plot shows the observed trends in the same color scale over this same interval. And it shows much stronger cooling in the Southern Ocean. We can pick a region over the Pacific sector in the Southern Ocean, and we can compare the magnitude of the cooling there over this 40+ year period. The observed value is clearly negative, in excess of 0.5 degree of cooling. And then in light blue, you see the distribution, the histogram of the values simulated by the individual members of the lens, the 40 members. And the 3 blue lines are the 3 new runs with the high resolution CSM. And you can see that they're still within the distribution of the lens, but very unlikely to be explained by the lens. In fact, there's 2 of these runs in the high resolution CSM the magnitude of cooling can only be explained by only 1 member in the lens. So there's only 1 member that simulates slight cooling over this interval. So there's something going on in this higher resolution version of CSM that produces more cooling in the Southern Ocean, albeit not as strong as observed. So I want to share some speculation on mechanisms. It's quite unsatisfactory. I've started looking at this a few months ago, but I thought I would share these results here to motivate some discussion. So this is the same plot I showed in the beginning, the magnitude of cooling, of warming, well, the SST change in the low resolution CSM and in the high resolution CSM, the ensemble mean 40 members for low resolution, 3 members for high resolution over the 21st century. So I'm back to the 21st century where we see this area of slight cooling despite the rest of the world is warming. So we can start looking at other responses in the ocean. Here I'm showing the changes in sea surface height, which reflect changes in the thermal structure of the upper ocean, and they're related to changes in winds and ocean currents. And we see that when mesoscale eddies are resolved in the high resolution CSM, the changes in sea surface height are stronger. The pattern is quite similar. Both types of models simulate a reduction in sea surface height to poleward from the polar front. So this area and this area are a reduction in sea surface height poleward of the polar front. So this means that the polar front is becoming stronger, and arguably a reduction in sea surface height is going to be mirrored by changes in the thermocline and upwelling, and it will produce more cooling. If we look at zonal currents, we also see that there's a lot of meandering. If you notice in the previous plots, the changes in sea surface temperatures show a lot of meandering, which is the same between all 3 runs. So resolving eddies and meanders in the Antarctic circumpolar current influences SSTs at very small scales. So here are the changes in zonal velocity over this 100-year period. And we also see the same features, like stronger velocity change with an accelerating or an increase in zonal wind velocity in the higher resolution version of CSM in that area in the Pacific sector where the cooling is more pronounced. If you notice, these areas of stronger currents coincides with the area where there's a gradient in the changes in surface height, consistent with geostrophy between sea surface height and the currents. If we look a little deeper, and this is the last result that I have, if we look a little deeper into what's going on with the currents, we see that there's actually a shift in the polar front equatorward. So this is quite counterintuitive, and I don't have an answer for why this happens, because the westerlies over this interval increase in intensity and shift forward, yet the polar front moves equatorward. And I'll show you where you can see that. These orange curves are the sea surface height in these 2 in two intervals over the 21st century. The dotted line is the first half, and the full line is in the second half. And this is a way to show what these changes in sea surface height represent. They actually represent an equatorward shift in the later half of the 21st century of the polar front here, characterized by this pronounced gradient in sea surface height across the Southern Ocean. It coincides with the area of stronger zonal currents, the Antarctic circumpolar current, which also becomes stronger towards the poleward front. You can see that this dotted line is the first half of the 21st century, and this solid line is the second half. I just realized that I inverted the order of high resolution, so high resolution now is on the left, not on the right. If we go to the right, we see the same changes, very similar changes in the low resolution version of CSM, but not as strong and not representative of a shift in the polar front. So we can imagine that if the polar front is shifting equatorward, it's bringing colder waters, colder polar waters, equatorwards, producing the cooling. So I know this is a very incomplete explanation, and yet I haven't explained why the eddies play a role. Arguably, ocean eddies play a role in these distinct oceanic responses to changes in the westerlies. So increased resolution leads to simulation of Southern Ocean cooling under greenhouse gas forcing. The cooling over the South Pacific sector involves an equatorward shift in the polar front. It's likely due to resolving ocean eddies, but recall that the atmosphere model is also higher resolution, although I checked and the changes in the westerly winds are comparable in magnitude between the two versions of the model. The full mechanism is still not clear. This cooling in the Southern Ocean in these simulations emerges in 21st century relative to internal variability. During the current last 4-year observational period, it's not as strong to be distinguishable from internal variability, but it could explain the observed cooling trend. Recall, the magnitude of cooling that the higher resolution version of CSM simulates over the last 40 years can only be explained by only one member of the large ensemble. So we have 2 new runs that can only be explained by one member. So what are the chances of that happening? And with that, I'll stop and take any questions.
Because of timing, we just take one question. Haiyan, go ahead. If you have any other question, just ask Pedro offline.
Pedro, thank you for the nice talk. I'm just curious whether you have looked at the AMOC, compare the temperature trend difference, whether and see whether it's connected to the AMOC.
It's a good question, Haiyan. I haven't thought about it, but a weaker AMOC should produce warming in the Southern Ocean, right? So, and in both simulations, I know
yes,
that
but I think the high resolution. I haven't checked Ting Chang's paper, but I remember there's that comparison of high res map looking at the lack of spatial coherence in the high resolution simulations, and I wonder whether the AMOC behavior can be quite different in the high res.
Yeah, it's a good. I'm gonna have to check. Thanks for pointing that out. Yeah.
Right, thank you. Move on to the next talk. Next talk will be given by Shinen Hu.
Can you all see the full screen?
Yes.
Okay, great. Hi, everyone. So even though I mentioned the causes and the consequences of Indian Ocean warming in my talk, but actually the majority of today's talk will be about the Indian Ocean warming itself. That work is in collaboration with Richard Seeger And then I will briefly mention my earlier work about the consequence of Indian Ocean warming with Alexei, and also another recent work led by my student Yiqun Tian and in collaboration with Clara Deser about the cause of Indian Ocean warming. Indian Ocean is unique. It sits in the deep tropics, and the entire Indian Ocean is characterized by warm sea surface temperature that's close to the convective threshold, which means that even if you have a small increase in SST over the Indian Ocean, it can potentially be translated into an increase of convective rainfall and therefore affects the global climate. So now if you look at the Indian Ocean SST as a function of time, you will find it closely tracks the global mean surface temperature, right? So it has been persistently warming, especially after the 1950s. And since then, it has been warming by about 1 degree. So now in terms of spatial structure, almost the entire Indian Ocean has been warming robustly, with the peak magnitude along the equator. And so across different data sets, even though there is some disagreement in the tropical Pacific, but it seems that they all agree on the fact that the Indian Ocean has been warming faster than the tropical ocean on average. So given the strong Indian Ocean warming, there have been a lot of studies trying to understand the impacts of Indian Ocean warming. And here I listed a few examples. In the next few slides, I will show you 2 examples in particular. So first of all, North Atlantic Oscillation. So in the second half of the 20th century, there was an upward trend in the NAO, which has drawn a lot of attention because it has influences on the European hydroclimate. So the Holling et al. Basically used the AGCM simulations and demonstrated that the upward trend in the NAO index within this time period was primarily driven by the Indian Ocean warming. And the next example, the Sahel. So again, in the second half of the 20th century, the Sahel region has experienced a multi-decadal drying trend, right? So, and there are a couple of studies using the AGCM simulations with different models, and they all find that the Indian Ocean warming can potentially cause the drought of the Sahel region through the modification of the worker circulation. So a few years ago, I did some relevant work along the same line, but we argued that the impact of Indian Ocean is actually beyond on the atmosphere. It can influence the Atlantic Ocean through the air-sea interaction. So on different timescales, the impacts are different. So on short timescales, the Indian Ocean can induce a positive NAO associated with the westerly wind anomalies south of Greenland. So acting on top of the climatological westerly jet stream, this westerly wind trend can potentially lead to a local cooling through the Ekman transport and also the enhanced turbulent heat flux. So we actually found that this mechanism can potentially explain about 90% of the observed North Atlantic warming hole. So on longer time scales, we find that the Indian Ocean warming can modify the tropical worker circulation and suppress the rainfall over the tropical Atlantic and the Sahel, and therefore increase the salinity over the tropical Atlantic. So then the tropical salinity anomaly can be transported northward by the climatological ocean circulation, and eventually the North Atlantic becomes saltier, the AMOC becomes stronger. So that process takes several decades to complete. So, but all the mechanisms I propose, they all started from the fact that the Indian Ocean has been warming faster and causing the local rainfall change and affecting the global teleconnections. But that idea has actually been challenged 20 years ago by multiple studies. So here's one example from Claire's earlier work by analyzing the COADS ship-based data and then looking at the epoch difference between the earlier period and the latter period. So if you are thinking about the long-term trends, you need to flip the sign over here. So the top panel shows the cloudiness change. And basically in the Indian Ocean, you see the cloudiness increase in the western part, but you see the decrease signal over the eastern part. So on average, maybe it's around 0. And interestingly, the most robust increase of cloudiness is seen over the tropical Pacific. So then they also look at the sea level pressure data also from the ship-based measurements. And basically it's consistent with the cloudiness change, and where you see the cloudiness increase over the tropical Pacific, it's associated with the sea level pressure decrease. And over the Indian Ocean, sea level pressure actually increases. Again, here you need to flip the sign for the long-term trend, right? So it really raised the concern that if the Indian Ocean warming has indeed affecting the global atmosphere, so why we couldn't see consistent signal in the atmosphere right over the Indian Ocean, right? Why the sea level pressure increases. So, but one thing I need to mention is that that works were completed 20 years ago. So at that point, we don't have sufficient data for the really for the long-term trends. And this is the Indian Ocean relative sea surface temperature, and basically with the tropical mean SST subtracted. And so that's because in the tropics, it's the relative SST that's most relevant to the rainfall change, which is the so-called warmer gets wetter mechanism. So now we have more than 20 years of more data so that we can revisit this problem, looking at the long-term trend in the relative Indian Ocean warming and its impact on the overlying atmosphere. So here we are doing similar type of analysis, and this is from the ICOADS ship data, which is updated version of the COADS. And the first figure I show you is the cloudiness long-term trend over the past 7 decades. And over the Indian Ocean, you see the general cloudiness increase in the western part and southern part, and there's some cloudiness decrease over here. And on average, now it's positive. But the general structure is very similar to Clara's earlier results. And in the tropical Pacific, surprisingly, we still see quite a strong increase of cloudiness in the tropical Pacific, which is also looking similar to the results earlier. Right, but there are 2 caveats I should mention about the tropical Pacific. And first of all, the tropical Pacific, there is a strong internal variability that can potentially contaminate the long-term trend in observation. So to account for that, we normalize this long-term trends with the local standard deviation. So, and basically the middle panel shows the signal to noise ratio in terms of a cloudiness trend, right? And in that case, you see more robust signal now over the Indian Ocean and the less robust over the Pacific compared to the top panel. So, but another caveat is about the data availability. The bottom panel shows how much fraction of the 70 years of the ship data is available at each grid point. So where you see red color, it means 100%. So the data is complete. And the interesting thing is that the area where you see the strongest cloudiness increase over the tropical Pacific is collocated with the area with not much data available. So where you see blue colors, it means that there is a less than 50% data available to compute the long-term trend. So we really need to be careful for the results from those blue area. And from the Indian Ocean, it seems that the data is almost complete for majority of the Indian Ocean. So I would think the cloudiness increase signal is more robust, at least compared to the Pacific. So then we also look at the sea level pressure change, again, from the ICOADS ship data. And consistent with the previous results, we see the sea level pressure increase instead of decrease over the Indian Ocean. And over the tropical Pacific, we see the sea level pressure decrease, also consistent with the result 20 years ago. And but on top of this panel, I highlighted those crosses, highlighting the areas with more than 30% of the data is missing. So, and interestingly, those areas co-located with the area we see those blue colors, sea level pressure drop. So that's why we took a look at another data set on the sea level pressure product developed by the Hadley Center. And in this case, we are looking at the same time frame, the long-term trends in sea level pressure. And over the Indian Ocean, it's more or less consistent. You see the sea level pressure increase. But the tropical Pacific is very different, and you even see the opposite sign. So if from this product within this time period, you see the sea level pressure increase over the tropical Pacific with even stronger magnitude than the Indian Ocean. Then putting this figure in a broader global context, you actually see the tropics generally has a sea level pressure increase, and the higher latitudes have a sea level pressure decrease in both hemispheres. And in other words, over the past 7 decades, this data tells you that the air mass has been migrating from higher latitudes equatorward towards the tropics in general, right? And this phenomena has been reported by other modeling studies as well on the global warming. So the bottom line here is that, yes, we do see the sea level pressure increase over the Indian Ocean, but that sea level pressure increase is weaker than the, for example, tropical Pacific. So then this result is at least not inconsistent with the fact that Indian Ocean has been warming faster. So then the question is, what caused the enhanced historical Indian Ocean warming, right? So this work is led by my PhD student, Yichun Tian, in collaboration with Clara, and we are analyzing the CESM1 large ensemble simulations and all forcing and all but one forcing experiments. And basically, Yichun found that the biomass burning aerosol is the primary driver of the enhanced Indian Ocean warming seen in the all forcing experiments. And I should have mentioned that in the 2 panels shown here is the relative SST trend with the tropical mean being subtracted. So the red color means that the Indian Ocean has been warming faster than the tropical mean. And you can see the all forcing experiments basically show consistent results with observation. And 80% of that relative warming comes from the biomass burning aerosol change. So the bottom panel here shows the long-term trend in the BMB aerosol optical depths. And as you can see that the Indian Ocean has experienced a long-term reduction in the biomass burning aerosols, in contrast with the tropical Pacific and Atlantic, where the biomass burning aerosols have been increasing with time. So as a result, you see the relative Indian Ocean warming. So now if you overlay this kind of a pattern on top of a uniform warming due to global warming, for example, you will start to see the enhanced warming over the Indian Ocean. So I don't have time to dig into details about this, but Yichun is planning to present this work in the CESM workshop in June. So if you're interested, please come to that talk or poster. So this is my final main slide, and the question we ask is to what extent our climate models can reproduce this enhanced Indian Ocean warming. I showed the results from CESM1, so how about the rest of the models? And this is the figure I grabbed from Lei Zhang's result 3 years ago, and they are looking at the CMIP5 multi-model mean the sea surface temperature trend as a function of longitude along the equator, and which is shown as a red line. So some models may do better than the others, but on average, multi-model mean shows almost a uniform warming along the equator, in contrast with the observed trends where you see the zonal difference clearly. So more recently, we look at the CMIP6 the model results as well, and basically we see the very similar the response, and the Indian Ocean warming didn't really stand out from the tropical ocean warming in general. So now if you look at the inter-model spread, you would find that for the models with the stronger Indian Ocean warming, they tend to produce a stronger tropical ocean warming in general as well. So in those different models, they fall onto a one-to-one line here, highlighting the fact that the relative Indian Ocean warming is close to 0 for all the models. So, and then if you compare with observations, they fall on the lower part of the this one-to-one line, which means that Indian Ocean has been warming faster than the tropical ocean. So that raised the question that what made the models unable to reproduce the enhanced Indian Ocean warming. So it could be internal variability. So in the observed trends, the multi-decadal internal climate variability could potentially contaminate the observed trend. And then it could also be due to the model bias in responding to the external forcing. So for example, if the model is the El Nino-like response in the tropical Pacific, which means that the relative Indian Ocean warming would be weaker because of the warming elsewhere, right? So, and it could also be the uncertainty in the external forcing. So if we indeed find that the biomass burning aerosol is the main driver of the enhanced Indian Ocean warming, as we all know, the aerosol forcing is not well constrained in the historical period. So if those kind of aerosol forcing is underestimated, then we will see weaker like enhanced Indian Ocean warming signal in climate models. So in the next few years, we plan to refine what is exactly the cause of the models. So it's critical because if the models cannot get the enhanced Indian Ocean warming right, it means that all the climate impacts related to the enhanced Indian Ocean warming won't be reproduced by climate models. So here is just a quick summary. Because of time, I think I will just leave those take-home messages here and take your questions. Thank you.
Because of the timing, so we move on to the next talk. If you have any question, you can ask Shinen online or send him an email afterwards. Next talk will be given by Jerry.
We'll see if we can do an in-person talk here. Last two are in person, so Claire and I get the in-person award, I guess. Perfect attendance, right? So I want to acknowledge collaborators on this work, John, Sasha, Antonetta, Julie, and Aishu. And since we're going to be talking about effects on the interdecadal Pacific Oscillation, or IPO, connected to the Australian bushfire smoke, let's just look and see what the IPO may have been doing over the last few years. Supposedly. Hello? Hello? Try on this side. Is that okay? 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 Is it okay? All right. I'm getting a thumbs up, so that's a good sign. So, of course, the IPO was famously in its negative phase starting in about 2000, and that was associated with this kind of slowdown in the rate of global mean warming. Has been written about quite a bit. But around 2015 or 2016, there were a couple papers that were written making the case from observations that maybe the IPO had transitioned to a positive phase around that time period. And in fact, the IPO, if it was in a positive phase, it was consistent with this more rapid increase in the rate of global warming, because that's a kind of a well-known connection between the IPO positive phase, you get more rapid rates of global warming. IPO negative phase, you get kind of slower rates of global warming. And so we looked at some initialized hindcasts here from the DPLE. This is one example from taking the 2013 initial year and looking at the prediction for lead years 3 to 7 for 2015 to 2019. And this is the prediction here, and you can see that the model is predicting for this time period positive phase of the IPO for this time period. If you look at the verifying observations, average from 2015 to 2019, you also see this kind of positive phase of the IPO compared to persistence, which was persisting in the negative phase of the IPO. So there was some indications from observations and from these initialized hindcasts that perhaps the IPO was trying to transition to positive around that time period. So what could be the physical processes and the mechanisms that are producing this kind of behavior with the IPO? And one of the things that seems to be important are these off-equatorial ocean heat content anomalies in the Western Pacific. So if you look in this upper right panel here, you can see these two boxes are drawn where we're going to be looking at these off-equatorial heat content anomalies. And that pattern there is just kind of a generic IPO positive phase. That's kind of the pattern from the second EOF of low-pass filtered sea surface temperatures. And the next panel down there in the middle right is the PC time series that often is used as an index for the IPO. And the fact that you may want to be interested in trying to predict something like this is indicated by that lower right panel where we correlate that PC time series with observed precipitation. You can see there's various pattern anomalies of precipitation that many of which we've been seeing over the last 5 to 10 years. And so there is interest in trying to do a good job in analyzing it. So when you look at the observations, in this case, this is a representation of observations. These are the initial states from the DPLE. And it's also consistent with other reanalysis ocean observation data sets. You can see that for these two areas, when the IPO transitioned from negative to positive here in the 70s, you started seeing the off-equatorial heat content dropping. When it transitioned from positive to negative around the late 90s, it started increasing again. It was at pretty high values here going into the 2000s, and then we got the 2015, 2016 El Nino and started to drop again. And the fact that we think there's some connection possibly between INSO on interannual timescales and the IPO on interdecadal timescales is that this transition from negative to positive occurred right around the time of the 72, 73 big El Nino event. This transition from positive to negative occurred around the time of the 2-year La Nina from 98 to 2000. And then this most recent apparent triad of transition was the 2015-2016 El Nino. But there's only a few realizations, frustratingly few realizations of these decadal timescale phenomenon observations. So to try to get a better handle on this, we were going into model world. We were looking at the 1800-year control run of CSM1, composite IPO transitions. And for this time period, we got about 50 cases of each, positive to negative, negative to positive. And if you look at these composites over here on the right, you can see that this is the composite IPO index here, the blue line, going from negative to positive, and by construction it crosses zero here, lag zero. This is 5 years before the transition, 5 years after the transition, and these colored lines here are these off-equatorial ocean heat content values, and you can see they're a bit above normal here before the transition, and then they drop at the transition and go below normal. And conversely, for the positive to negative transition, you can see the IPO index goes from positive to negative here, and the off-equatorial Western Pacific heat content is below normal and then starts recharging after this transition. And so that at least seems to be somewhat consistent with what we saw with those limited samples from the observations. And the tie to INSO is that if you look at El Nino and La Nina events around the time of these transitions from negative to positive in lower right, there's a better chance for an El Nino transition happening from a negative to positive IPO compared to La Nina. And then that lower right panel there is the better chance of a La Nina occurring around the time of transition from positive to negative IPO. So there are these kind of interesting possibilities that you have this timescale interaction, and you can imagine this is kind of analogous to timescale interaction with MGO vents, westerly wind vents on subseasonal timescales, providing the triggers to El Nino transition. So it is kind of interesting that these things could actually be happening in the climate system. So okay, this all looked pretty good. This seemed to be a fairly consistent story. We had this, these kinds of big drops in off-equatorial heat content here associated with this 2015-2016 El Nino. We seem to have some evidence that the IPO was trying to transition. But then this happened. So the off-equatorial heat content rebounded around 2019. And you can see the increase there. And if you look on the far right there, you can see that the globally average temperature trends or the rate of warming actually flattened out, which is indicative of a negative phase of the IPO as well. So what happened? Well, one thing that happened right around this time when this all seemed to kind of go in ways we didn't expect were these huge bushfires in Australia. And it produced these amazing satellite images. You can see here these ones on the left are from showing southeastern Australia. See these gigantic smoke plumes going out across the Pacific. And this animation of black carbon transport from NASA here on the lower right shows that this smoke was actually getting entrained in these various synoptic systems going across the subtropical Pacific, basically. And you see the smoke is making it all the way over to the off the coast of South America. So it's at least making its way across the Pacific. And so the question is, did this smoke from the bushfires disrupt this IPO transition from negative to positive that seemed to have been trying to occur around 2015 and possibly externally force a 3-year La Nina and return the IPO to a negative phase? So to look at this, we're going to look at 2 sets of initialized hindcasts with CESM2. Both are initialized in August 2019, right around the time the bushfire smoke started. Run them from 3 years to July 2022. Each is in 30 ensemble members. We're going to show annual averages mostly from August to July. And we're going to have this differences as smoke minus no smoke. In other words, the simulation with the Australian wildfire smoke minus the reference simulation where there was no smoke. We're differencing these two, which is the really nice benefit of this is that we can directly remove the drift from these 2 simulations because we're assuming they're both drifting in the same way. And so these anomalies should provide a pretty accurate representation of what the model's trying to do. The bushfire smoke emissions are from GFED, which is a aerosol observed data set. So here's some results that John Fasullo published, and he has a couple papers on this in 2021 and 2022, looking at this kind of first year. And so the plots here on the left side are showing the aerosol burden in the model. This again is the smoke minus no smoke. And you can see these big kind of orange and red colors here coming off of Australia, and you see those orange colors going across the Pacific, which is what we seem to see from the observations. And then that continued on to December 2019 in that middle panel, lower left panel. By February 2020, the smoke's starting to kind of wane, and by March 2020, the wildfires were pretty much over. And so it's kind of by early 2020, this is pretty much done. The fact that this smoke was behaving in this way, there's a paper by Loeb et al. From MODIS observed data showing that that is not far off from what the model experiment is trying to show. And if you get these smoke particles getting all the way across and getting into the cloud decks off the coast of South America, you can expect that you're going to have increases of cloud albedos. And you see these orange and red colors here off the coast of South America. And what's happening, of course, these smoke particles go over there, they provide more cloud condensation nuclei. You get smaller and more numerous cloud droplets, which produces brighter clouds. And so that's what's happening in the model, and that seemed to also be seen in the series data from satellite observations as well. But now we can look beyond that kind of first year, and this is going to have an effect on sea surface temperatures, and sure enough it does, because if you look here at the first year, you can see the area here where you had the increased cloud albedos, you're getting reduced solar at the surface, and these sea surface temperatures are cooling off here in this model, smoke minus no smoke difference. If you go to the next year, these actually are growing and spreading all the way across the Pacific, and by the third year, they've actually grown even more, and now they're extending from the southern hemisphere, almost mid-latitudes, all the way across the tropical Pacific. And if you look at a kind of a comparable period in the lower left from observations, this is October 2020 to September 2022. You see a similar kind of pattern of a huge area of anomalously cold water there in the kind of the eastern Pacific. But the interesting thing about this is if you think the smoke was the cause of this, the smoke was pretty much done by the end of that first panel up there. So in the second and third panels, lead years 2 and 3, where these SST anomalies are actually growing in area and intensity, and the smoke's not causing that. So what's causing this this kind of persistence and these growth of these anomalies? And so when you look at the sea surface temperature anomalies, you can see that not only is the cool water going all the way across the Pacific, you're starting to see warm water over here over the maritime continent. You're starting to mess around with the Walker circulation. You're getting low-level convergence going on over there, coming off the Indian Ocean into the maritime continent, and that should be giving you more rainfall over there. And indeed, if you look at the rainfall anomalies here in lead years 2 and 3 on the left side, you can see that over these cooler SSTs, you're seeing these blue colors are anomalously or negative precipitation anomalies in this model experiment, smoke minus no smoke, over the area where you get kind of warmer sea surface temperatures, where you get more low-level convergence, you're getting increased precipitation. And the fact this could have been happening in observations, you can see here in 2020, 2021, you get this increased precipitation over the maritime continent, decrease over the western tropical Pacific, and the same in 2021 and 2022. So this seemed to have set off at least, or probably at least, 2 sets of coupled feedbacks that were able to maintain and grow these sea surface temperature anomalies. The first has to do with this kind of increase in precipitation convection over the maritime continent. And of course, when you start doing that, you affect the water circulation, you get stronger descent over the eastern Pacific, you strengthen the subtropical high, and that's what you see here in the smoke minus no smoke experiment. The red colors here are a stronger subtropical high that persists all the way through the forecast period. The black arrows here are highlighting what these little white surface wind stress vectors. You're basically getting more southerly flow on that east side of the anomalous subtropical highs there. And just to highlight that, this is the meridional wind stress, and the red colors here are basically positive or south to north meridional wind stresses. And again, the black arrows are highlighting the fact you're getting this huge area in the southern hemisphere of anomalous northerly flow, which would have 2 effects. One would be an advection, and this you'd be advecting cooler water up into this tropical Pacific, as indicated by these papers by Zhang and collaborators. The other one, of course, is the the west feedback that's part of the South Pacific meridional mode that could also get these cooler sea surface temperatures up into the tropical Pacific. Okay, so that's one set of coupled feedbacks that would be associated with what was going on in the tropics. The other one is more connected to the IPO, and this is where we've looked at these composites from the model again, and this is when we're looking at the Western Pacific and looking at U component wind stress. The blue colors here are anomalous easterly or stronger trade winds blowing all the way across here. The blue arrow here is kind of highlighting these anomalous easterlies coming all the way across into the Western Pacific. And you're getting anomalous westerlies to the north and south, these kind of anomalous high circulations, which is kind of a gill-type response to this negative convective heating anomaly that we presume that's going on here over this, where you have reduced precipitation and cooler SSTs here in the Western Tropical Pacific. And to pin that down, we can actually run an experiment with an atmosphere-only model here in the lower right, where we put in a negative convective heat anomaly, look at the wind stresses, which is the wind stress anomalies of the colors here. And in this atmosphere-only experiment, just with the convective heat anomaly there, the negative anomaly, you're seeing you're getting stronger easterlies and the stronger the westerly anomalies to the north and the south. And what that's going to do to the ocean, of course, is you're going to get Ekman convergence going on right about 15 north and 15 south, and Ekman pumping is going to go on in this off-equatorial region. That's going to put heat down into the subsurface ocean, which is, of course, a hallmark of this mechanism that we think is important for sustaining the IPO on decadal timescales. If you're looking at the smoke minus no smoke experiment here in the upper left, you see a similar kind of thing happening. Again, this is U component wind stress anomaly, so the blue colors are enhanced easterlies. Red colors are anomalous westerlies. Get this gill-type response again because we've got this negative convective heat anomaly over here. And that also should give us this Ekman pumping going on at 15 north and 15 south and increase off-equatorial ocean heat content. So let's see if that's actually happening. Let's go down here, and this is heat content, the smoke minus no smoke experiment. The red colors are buildups of heat content in the off-equatorial Western Pacific that's going on as a result of this kind of wind stress forcing connected to these convective heat anomalies over here. And there's some evidence of that going on in the observations, where you get this, especially in the southern hemisphere that Kevin was just talking about, kind of big buildups of off-equatorial heat content here and some in the off-equatorial Western Pacific north of the equator. Okay, so that all went by kind of quick, so let's try to summarize this kind of chain of processes that I was just talking about. So if you start out with the smoke coming off of Australia, it's evected across the Pacific. This is happening in the subtropics, so it's A lot of it's not rained out. A lot of it's making it all the way across to the coast of South America. And subtropical South America, that brightens the clouds off the South American coast. That reduces incoming solar at the surface. That means you get less incoming solar at the surface. The sea surface temperatures cool off. The South Pacific ice strengthens. The trade winds strengthen. And you get this cooler water that's moved up into the equatorial eastern Pacific that then triggers Bjerknes feedbacks, and that spreads the cool water right across the Pacific. And that gets reduced sea surface temperatures and precip in the western equatorial Pacific. And that means sea surface temperatures and precip increase over the maritime continent, and the Walker circulation strengthens. So that all sets up these two sets of coupled feedbacks that make this pattern grow and persist past the initial smoke impulse. This strengthened Walker circulation, of course, the South Pacific high becomes stronger. That gives even more northward surface wind stress in the Southeast Pacific. Even more cool water gets into the equatorial Pacific, and that keeps going. There's nothing that's going to stop that until something happens to cut off this convection that's going on in the maritime continent. The other one is this negative convective heat anomalies produce this gill-type response that gives you the off-equatorial westerly wind stress anomalies. You get the Ekman pumping from the wind stress curl down into and putting heat content into the off-equatorial western Pacific near 15 north and 15 south. And that sustains the negative IPO and also contributes to this reduced rate of global warming that we've been seeing. So then the question is, what's going to happen? So in past negative IPO events, they tend to end with an El Nino event and transitioning back to a positive IPO. So we'll have to see what happens in the next couple of years to that. Thanks.
Thank you. Okay, let's take one quick question.
Thanks, Jerry. Appreciate the talk. Did you look at subsurface ocean heat content? I know that you're invoking a lot of the heat content mechanisms, but I'm wondering if you had cross sections of smoke minus no smoke.
No, I haven't looked at that yet. We just looked at kind of the average heat content, especially for that Zheng mechanism, because this advection mechanism, he thinks it's the subsurface water just beneath the surface that actually gets advected up from the subtropical South Pacific into the equatorial waveguide. So, yeah, that's something I think we could look at, is look at some cross sections.
Cool, thanks.
Yeah.
Thank you. Okay, now our last talk will be given by Clara.
Okay, can you hear me? All right, I'll keep it brief. Thank you for sticking around. Now for something completely different. We're going to look at marine heat waves and cold waves, and specifically investigate how will the intensity and duration of these marine heat and cold waves change in the future. Adam and a whole bunch of NOAA people are collaborators on this project. Okay, whoops. Okay, that works. Okay, so of course there are two components to future climate change. One is background warming, and one is changes in variability. So it's a no-brainer that as the oceans warm, marine heat waves will become more intense and warmer. So that's the what's the adage? A rising tide lifts all ships. So that's not so interesting to look at. So we have focused on how changes in variability in the future may impact the intensity and duration of these marine heat waves. And of course, large ensembles are a really good way to look at this because you have so many samples that you really need to look at whether there really are robust force changes in variability. So we have used 7 different initial condition large ensembles, and we're looking at the time period 1970 to 2100. For this study, we've picked 4 CMIP-6 model large ensembles and 3 of the CMIP-5 generation, and they have between 30 and 100 members each. So I'm just going to outline our procedure that we used to identify marine heat waves and cold waves and then to look at their future changes. So this is what we've done. So for each grid box of a given model large ensemble, we're operating on the monthly mean SSTs as a function of time. So the first thing we do is we remove that background warming by subtracting the ensemble mean from each member at each time step. So I call that little I SST, internal SST, as a function of time. And then we pool together all the ISST records from all the members of a given large ensemble, and then we identify the seasonally varying thresholds. In this case, we use the 10th and 90th percentile. We've also used the 5th and 95th, doesn't matter too much. And we compute these thresholds for separately for these three 31-year periods, just to get an idea of course, how things change over time. And then we define a marine heat wave when the ISST exceeds that 90th percentile threshold, and similar for a marine cold wave. And then we composite all the samples of marine heat waves and cold waves, and we composite their intensity in degrees C and their duration in months for each time period. And just to give you a ballpark number of samples here, so say for the 100-member CESM2 large ensemble, we have, according to this recipe, over almost, 3,700 samples of marine heat waves, and the same for marine cold waves in each period. So we have really robust sampling with which to look at forced changes in the variability. Okay, so I'm going to illustrate things first with the CSM2 large ensemble, and then I'll show you the intermodal comparison in a moment. So this is the composite marine heat wave intensity for these three different time periods according to the protocol that I just described. And you can see, of course, hot spots, equatorial Pacific, and then along the Kuroshio extension and along the Gulf Stream in all three time periods. And then you can definitely see that as time goes on, that at least in the equatorial Pacific, there is some evident decrease in the strength of these composite marine heat waves. So to show that more clearly, we can look at the difference maps. So here I'm showing you the difference relative to present day, 1970 to 2000. And on the left would be the mid-century difference, 2020 to 2050. And on the right is the end-of-century difference. So importantly, the gray shading indicates where these force changes in the intensity are not significant, and that we've applied this false discovery rate test to the t-test at the 5% confidence level. So mid-century changes, there are certainly patches of significant increases in marine heat wave intensity on the order of a couple of tenths of a degree C in the composite. And then by the end of the century, you can see for this model, there's a decrease in the intensity in the tropical Indian Ocean, the equatorial Pacific, the parts of the tropical Atlantic, and parts of the Southern Ocean. So it's a messy pattern. One might expect in the future, as the mixed layer shoals stratification increases, you might get more intense variability and more intense heat waves. But that is certainly not ubiquitous here in the CSM2 large ensemble. So that's intensity. Now I'll show you the same maps for duration. So again, remember, we're using monthly mean SSTs, so you have to, we're using a coarse metric here. But these are the results for the duration of marine heat waves in these three different time periods. And here by eye, you can really see that there's a reduction in the duration by the end of the century in the tropical Eastern Pacific. And then here are the difference maps. Again, gray shading denotes insignificant changes. And mid-century, not too much going on. But by the end of the century, there's a lot of blue. So marine heat waves are becoming less long-lived. The North Atlantic is a notable exception. So that's the CSM2 large ensemble. Let's now, we're going to look at that end of century difference map, and I'll show it for all 7 of the model large ensembles. So that's just an easy way to do the comparison. So here it is, and in the upper left is what you saw before, the CESM2, and that little number on the upper right is just denoting the fractional area of the global oceans that have a significant forced change in the intensity of marine heat waves due to internal variability. And the models are, there is no single answer here. There's a lot of model dependence in the pattern and the magnitude and the amount of area that has a significant change. But if we sort of step back, maybe there are some general themes that there's tends to be in the extratropics in some of the models an increase in the intensity, and in the equatorial Pacific in some of the models a decrease in the intensity. So now I'll show you the results for duration. And again, you saw CSM2 in the upper left before, and now here are all the other models. And I would say here there's more blue than yellow. So on average, the models in many regions do project a shortening of the duration of marine heat waves. There are exceptions in the Arctic where there's a lot of model uncertainty. Okay, so nothing profound at all, but I should say people haven't really isolated this component of changes in marine heat waves before. I think it was just waiting to be done, and that's what we've done here. But the thing I'm most interested in is actually to show you and then wrap up, is whether there's a role for changes in ENSO. Obviously, you saw a lot of things going on in the equatorial Pacific, so it raises the question, and we know from so many studies that ENSO is projected to change in the future. So we decided to repeat this whole analysis just for ENSO neutral years. And I can give you the details. We've explored different ways to define ENSO neutral months. And what I'm going to show you here is that if we identify a marine heat wave at a particular grid box and month and year, we will put it in the ENSO neutral bin if the preceding 6 months and the concurrent month are all ENSO neutral according to the leading 2 PCs of tropical Pacific SSTs. So I think it works pretty well. Okay, so this was the result for all years. Now I'll show you the duration changes for just the ENSO neutral samples. And this is where large ensembles are really valuable because we cut our sample size way down, but we still have probably 1,000 samples or something in this 100-member ensemble. So it's pretty much all gray, like it goes away. And I just think we haven't recognized that ENSO changes, whether they are, credible or not in the model projections. They are going to exert a huge influence globally. And I think this is just an important thing to keep in mind, that ENSO, is we really have to grapple with understanding how credible our ENSO projections are for things like this, consequences for marine heat waves. So it's very dramatic for duration. Now I'll just show you the last result, which is looking at the ENSO-neutral samples for intensity. So here are the intensity changes just for the ENSO-neutral samples. And I'm going to toggle back and forth one time. So this is ENSO-neutral. This is what we had for all samples. And now we go back to ENSO-neutral. So there's a lot less that is significant in the ENSO-neutral samples, but there are regions that do survive or that do maintain a forced change in intensity. The Arctic is especially notable, but there are some really interesting patterns in CSM2 that I have some speculations about, but don't have too much to say about them now. So I think that that is it, and I'll give you my conclusions. So initial condition, large ensembles provide a robust way to quantify future changes in any variability, but in this case, marine heat and cold waves that arise from changes in variability. And in general, that is the operating word here, if we were to find some commonality amongst the models, I would say that in general, there is projection for more intense marine heat waves in the exotropics and less intense in the tropics, and also expectation that their duration will be shortened except in the Arctic. I haven't shown you the results for marine cold waves. They're largely symmetric or similar conclusions. Changes in ENSO account for almost all of the changes in duration and most of the changes in intensity outside of the Arctic and North Atlantic that we noted in point number 2. And then finally, just to put this step back and put this in context, there are projected changes in variability, but they are small compared to what the mean state background warming does. So we have maps of how large the contribution of changes in internal variability is to the total change in marine heat wave intensity and duration, and it's generally under 10%, except in the Arctic and near Antarctica. So if organisms in the ocean can adapt slowly to climate change, then they're only going to be seeing these changes in variability. But if they can't adapt to the slow background warming, then that's going to be the main factor that will affect them in the future. Thank you for sticking around. Thank you very much.
Yeah, we need to get out here by 5 o'clock exact. So we have a couple more minutes. And
could do Rob.
The microphone is on. So I have a comment and a question.
Yeah.
If you didn't see it this morning, Fabrizio Falasca had a nice talk relating percentiles of a distribution to the moments of the distribution. And so, yeah, I think there's it could probably relate to the percentile-based metrics you're looking at to more things, simple things like SST variance. And it did stand out in some of your figures that these look like a lot of like what I've seen for like the SST variance.
Yeah.
So I guess you kind of answered it here, but if that was the case that it's due to variance, you'd expect the marine cold waves to have kind of the mirror image. Is that what you found?
Exactly, and we didn't want to presuppose that. And I think a lot of studies have just, looked at, as if it were a symmetric distribution. We're about to quantify if there really is any skewness or asymmetry in the cold and warm tails. Haven't done that yet, but to my eye, they look very symmetric, except in the far western equatorial Pacific, where marine cold waves, they can extend farther west, just like farther west. So there may be some regions where that is not the case. And there's definitely some asymmetries in the Arctic. It's quite skewed distributions. So thanks for that, Rob.
Okay, one more question, Jerry?
Yeah, so
I think
it seems like the duration changes were one of the kind of more notable results, and they're connected to ENSO, as you pointed out. So I'm trying to figure out physically what does that mean if the duration of a marine heat wave get shorter in a warmer climate? Is it related to the definition, or is there something physically that would make it shorter, do you think?
Well, I think in this case, we're just demonstrating that we've seen it in the CESM2 reference, large ensemble reference paper, that the ENSO cycle itself becomes the spectral peak becomes narrower and it shortens somewhat. And I think that's actually due to that La Nina events tend to not last more than 1 year in the future. So ENSO is shortening its life cycle, and I think that's what we're picking up in this change in marine heat wave duration.
Can I ask a question?
You may, Kevin.
We're going to be charged.
I've had my hand up for some time. Yeah, hi, Clara. I wonder if SST is the proper way to look at this, because I wonder if you shouldn't be looking at something like specific saturation-specific humidity, because if you have a 1 degree anomaly on top of, say, 27 degree water versus 25 degree water, the saturation-specific humidity is 15% more or 20% more. And the rainfall and the consequences in the atmosphere are much greater. In fact, I'm not surprised that the duration and the extent of the SST anomalies goes down, but the impacts on the atmosphere and the flooding can still go up.
Excellent. Thank you for that comment. I'm going to follow up on that. Great.
Okay, thank you.
Yep.
Now, we're very close to 5, so we just end our meeting for today. And for the people still here, we are going to go to understand. If you need a ride, just let us know. I have a car. We have quite a few others have cars.
Yeah, we don't actually have a reservation under the sun, so if you're there first, grab a table. I have space as well. And then tomorrow we have the joint session with the Earth System Prediction Working Group. At the moment, I think the plan is still to come here, but maybe keep an eye on your emails in case NCAR decides to have a late opening. So thanks. I'm sorry for the technical difficulties.
At what time are you going to start tomorrow morning?
9 o'clock tomorrow.
9 o'clock? Okay, thanks.
It's 48 inches, I think. Not 48.